Okay, good morning. So maybe today I'm going to stay on this side since I see you followed my request of yesterday to sit rather this side. So, okay, let us go. So this is what we did yesterday, and I have here, yes, a bit of recap. So yesterday we defined this notion of coherent germs. We defined the scaling. Okay, this typo, this should be epsilon n. Sorry about that. I will correct in the next version. And then, so we have these two parameters, alpha and gamma, which play different roles here. And so we stated this nice reconstruction theorem that says that if your germ satisfies this coherence condition, then there exists a distribution which is locally well approximated by the germ at every point x in this sense. Okay, and you have uniqueness when gamma is positive. Okay, I have some. Okay, there is one important special case, which is the following. So suppose that your coherent germ now has so positive gamma. So then we have seen, this is a general fact, that one way of approximating, of constructing the reconstruction is this limit. Okay, you remember I introduced this function rho. Okay, and then I defined this approximation. I proved that this converges and satisfies the reconstruction bound. Now, suppose that this germ has an additional property, so that in fact fx is not a distribution, but it is a function that I can compute at y, and moreover the function of two variables, fx of y, is in fact continuous. So this happens in some nice cases, not all cases, but this can happen in applications. And then, so if you apply a dominating convergence in this limit, you see that in fact this just converges to a Dirac mass at z, and therefore, so this is just fz of z, which means that the reconstruction can be represented, so it is a distribution, but in fact it can be represented as a function, which is z to fz of z. Okay. For example, this includes the Taylor polynomial, because if you think of it, when you compute the Taylor polynomial for y equal to x, all the terms of degree strictly greater than 0 cancel, and you remain only with the 0 degree term, which is just f of x. So this is a particular case of this general phenomenon. Okay, so this is one small detail. Now, I wanted to discuss again the phenomenon of non-uniqueness for gamma negative. So in fact, I want to discuss so how non-unique is the reconstruction. Okay, how many possible reconstructions do you have? Can you classify them once your germ is fixed? So suppose that you have one reconstruction, T here, which satisfies this with gamma negative, uniformly, blah, blah, blah. Then consider the space C gamma that we defined yesterday. So you remember these were this Bezoff-Hölder space with negative regularity. So maybe I can just show you the definition again, which should not be very far. Yeah, here. So you, at each point x, you compute the distribution on the scaled function, and then you require this to be bounded by epsilon to the alpha bar, which is negative. So you allow for explosions, but in a controlled way. Okay, so this is the space C alpha bar. And now I consider C gamma. So I add to T a distribution in C gamma. And so you see that by triangular inequality, so the same bound is still true for T plus D. Okay, so if T is a reconstruction, then T plus D is also a reconstruction for any D in C gamma. And vice versa, for any T prime second reconstruction of F, then you take the difference. Again, you have this simple triangular inequality, and you obtain that it scales like at most epsilon n to the gamma. But then again, this is the definition of C gamma. So it means that T minus T prime is in C gamma. So this means that for gamma negative, the reconstruction is unique up to an element of C gamma. So you don't have uniqueness, but at least you know how to characterize the multiplicity. Okay, so this plays a little role in this singular product business. So you remember we studied a function f in C alpha with alpha positive, and a function and a distribution G in C beta with beta less or equal than 0. We defined a germ which is this P, which is candidate to construct a product, and we proved that it is, well, actually I didn't prove it, I stated this theorem, which says that it is alpha plus beta coherent. Now, again, if alpha plus beta is positive, then the product is canonical, and this is called the Young product. If alpha plus beta is negative, then the reconstruction RP, we said, is not canonical, but again, it is unique up to an element of C alpha plus beta. Okay, and okay, at this point, yesterday I started to write something on the one-dimensional case. Okay, I mentioned this discussing with the Sumei. But okay, maybe I was tired. Maybe I didn't I didn't finish it. So I still think that this is interesting, but maybe I'll come back to that at the end of this lecture or during the third lecture, because this can be related to other details. So yeah. You see, I hesitate on this, but so let's go on, and then I promise we'll come back to this later. Okay. So now, chapter 2, models and model distributions. Okay, on this I have to make another comment. So I said yesterday that terminology here can be how can you say, a bit arbitrary. So I'm using words which Martin used in his paper, but the meaning is not always the same. So in the sense that you will see, I try to be as general as possible and to introduce new structure, new notions only step by step. Okay, so what I define as a model is not what Martin defines as a model in his paper. So sorry about that. Be aware of this. This serves as an introduction to the main ideas of a model, and then there are additional details which will be filled in at least partially during these lectures. Okay. Yeah, and by the way, this makes me think of another comment. So I told you yesterday, so this reconstruction theorem that I presented, I said is more general than what Martin did, because he actually proved it only for model distributions. So also here we try to do something more general, but the game is not just to generalize for the sake of generalization. So we don't want to lose power, okay? It's because the aim is always at the end to solve some equation, and for that you need the good estimates and the good notions, etc. So we don't want just to say, okay, this is more general than what Martin did, if you then lose and you can't do anymore what he did in the end, okay? So it's a bit of a risky game, and we'll see what comes out of it. So again, I told you that the reconstruction theorem can be applied to coherent germs, which form a large vector space. But in fact, this space is too large. You do not expect to need such a huge space when you solve an equation. For example, for a PDE, you never prove existence and uniqueness of a PDE using the space of distributions. It's too large. You always have some, I don't know, Hilbert norm, okay, some Sobolev base of whatever, okay. These are more efficient spaces to do estimates, and this is the case also here. At some point, we want to discuss some SPD with some fixed point, okay, and then one idea is to study germs which can be written as suitable linear combinations of a fixed finite family of germs, okay. So let me give you an example that you have already seen. So last week, so this is an example from the course of Sebastian Riedel. So it should be theorem 55 in his third lecture. So which is the construction of the rough integral. So you have alpha between 1/3 and 1/2. You have a alpha rough path, so the two levels of the rough path, and you have a controlled path. So I don't repeat the definition, so I expect you to have still at least a vague memory of this. And then with these ingredients, you can build this function of two variables, okay, which I could also call a germ. So Massimiliano calls this a germ also in the case of rough paths. And then, so you take the delta operator, and you realize that this is C3 alpha. Okay, I hope that, yes. Well, okay. I hope you remember what this means. So I write it because, so this means that you have psi st minus psi su minus psi ut bounded by t minus s to the 3 alpha, okay, when s is less than mu, less than t. And okay, so this is we discussed this yesterday. It's the analog of the coherence condition. So what happened here? Okay, and then the Seuil lemma applies, and you can define the rough integral, which is actually the unique continuous function I, which satisfies this property. Okay, so you see, the Seuil lemma applies to germs. Oh, okay, sorry, to functions in a certain space which we defined yesterday. And this has nothing to do a priori with rough paths, with controlled paths, etc. Okay, but how do you construct germs which are in this good space? So this is a way. This is a class of functions psi which have the good properties, and so it's something that you can give, okay, to the Seuil lemma in order to produce to apply, okay, to apply it. It's material for the Seuil lemma. And in a sense, the reconstruction theorem is the same situation. We want to produce germs which are coherent, but this is not so easy. Until now, we have only seen the Taylor expansion. Okay, I'm telling you that in fact, control paths generate coherent germs if you do this correspondence between in one dimension between the Series lemma and the reconstruction theorem, but in higher dimension that's a bit more complicated. So we are going to do exactly that. So we want to build analogs of X, the rough path, and of Y, the control path, in order to have a class of coherent germs, which again will be the space where we look for the solution to our SPD later. Okay, so again, pre-model. So this is a pre-models is another terminology which exists in other papers. This has nothing to do with that. It's just that it is weaker than a model. Okay, so if you don't like pre-model, this is a weak model, a yellow model. I don't know. So it's just a word. Okay, so let's see what this is. I said that we need a finite family of germs. So this is the first ingredient, pi. Okay, at least I'm using the same notations as Martin. And this is labeled by a finite index set I. Okay, and then you need a little bit of structure. So one thing that you need is a matrix valued function gamma. So this is a matrix in ij, where ij run in I, and it's a function of two variables x and y in Rd, which give this, how do you say, kind of change of basis relation. So when you move from x to y, so you can write the distribution. So remember that for fixed j and y, this is a distribution. Okay. Now, this distribution will be the sum over I of the distribution pi I at point x times this real number, gamma ij xy. Okay, so there is a relation when you go from the point x to the point y, and this is coded inside this matrix valued function. And you have this assumption, which is a homogeneity assumption on the pi's. For every I, you have a real number alpha I, and so there is a fixed phi in. So this is like the coherence assumption, but it is in the context of homogeneity, and you assume that you have this scaling when epsilon n goes to 0. Uniformly for over x in compact sets, etc. Okay, and you denote alpha bar as the minimum of these. We call them homogeneities. Okay, so this is the minimal homogeneity. Okay, if you already know a bit of regulative structures, you will recognize that this is a kind of a say subset. Okay, no, of the assumptions that you have for a model. Okay, so this is the minimal set of assumptions that I need for the next slide. So this will be the analog of X, of the rough path. And okay, let's give an example. So, but again, this is something we know. The family of classical monomials for gamma positive given by this forms a pre-model, and the matrix which gives the change of basis is just more or less the same as the model, as the pi itself, and this is just the Newton binomial theorem. But okay, this is nice because this allows to recover Hölder functions a bit later. Now, okay, this is the analog of the y. So we again model distribution is a terminology that Martin introduced, but here I'm using it in a, say, more in a weaker sense, let's say, for the moment. So fix this pre-model and a gamma which is greater than the maximum, not the minimum, but now the maximum of all the alpha I. Now you take a function from Rd to R to the I, so I is the index of the pi's. So you're considering some coefficients. Okay, let me jump to the last line. So what we want to do is to write a germ, which is, as I said, the linear combination of the pi's, and each pi will be multiplied by a coefficient fi of x. So notice that the coefficient also depends on x, so this is not just a finite dimensional space, it's an infinite dimensional space, but it's much smaller than all possible germs if you have fixed the pre-model. And now you assume that this function f satisfies these two properties. So this is just that it is locally bounded, and this is the relation with the pre-model, actually just with the gamma matrix. It has this bound. Okay, we just look at it for a few seconds. What can we say about this? I will show you why this is useful, and then we call F a distribution modeled by the pre-model, or simply a model distribution, and this is the notation to make clear that this depends on pi gamma. Okay, and so given these two ingredients, this is like the rough path. This is like the control path. We define a germ in this way. So again, remember this is still a distribution. So pi is a distribution, while f is really just a function. So it's a real number. Okay. Now what I claim is that if you do that, then you find a coherent germ, namely a alpha bar gamma coherent germ, where again, so remember that alpha bar is the minimum, so gamma is greater than the maximum of the alpha I, but it may be negative as well, so it's not, or it may be positive. Okay, and so we use, let's try to read this slide fully. So we have this re-expansion property, which is the key relation. Sorry. Okay. Now you consider the germ at z minus the germ at y. Okay, you write it like this. Here I sum over j. Here I sum over y. And for pi j z, I apply the re-expansion property. So I obtain pi iy, which I write here. And then, so this is fiy minus, and from the re-expansion property, I get this quantity here. Okay? So this is exactly what you find in the assumption of f over f. Okay? You see? So that's why this is a good idea. So it turns out that now, if you compute this over your scaled function, test function, so again, only pi I is a distribution. So this is applied, pi iy is applied to phi epsilon y times this real number, and then you estimate. So this is bounded by epsilon to the alpha I, because we assume this homogeneity on the pi's. And sorry, yes, don't forget the phi was fixed. Okay, this again, there was the assumption that you had one phi here with this property. Okay, and then by the assumption over f, you have this bound, and so okay, now if you, so what are we doing here? We are, maybe there is one step that I skipped. So So wait a second. I think that yes, we. I don't remember. So there is a small. So if you go to this, to that, you're not. Yeah, that's okay. That's it, probably. So you write this. This you write as epsilon to the alpha bar times epsilon to the alpha e minus alpha bar. Okay, now this is non-negative because alpha bar is the minimum, and then what you do is that epsilon to the alpha I minus alpha bar times z minus y gamma minus alpha I, you replace, so maybe this is typical of me getting lost in details. So this you can certainly, so this is also positive, but yeah, so it should work. So this is epsilon plus z to the minus y to the power alpha I minus alpha bar plus gamma minus alpha I, and so the two alpha i's cancel, and so yes, that works. Okay, so you need two non-negative exponents to do the trick, and this is, it works. Okay. Yeah, so you see, so this is the definition, so the property of coherence with the two exponents, now alpha bar and gamma. And you also have homogeneity. This is actually simpler. It's just the assumption that Fi was locally bounded, and the fact that now epsilon is 0, 1. So if you replace alpha I by alpha bar, which is smaller, you get an upper bound. And okay, then this means, okay, theorem if you want, that given a pre-model and a model distribution, this germ is alpha bar gamma coherent with homogeneity bound, and the exponent is alpha bar. And notice that here the two exponents, so alpha bar, are equal. So you don't have three exponents, you have only two of them, which is okay. Which is what also happens in Martin's paper. Okay. So this is supposed to be really very elementary, so I hope you could follow. Now, what comes next? Yeah, I have an example, which is again the classical one. So we're not going very far yet, but this is instructive, I think. So consider again the classical pre-model of the polynomial, the monomial functions. Then see what is a model distribution in this setting. So we have F, so the index set is just these multi-indices. For every I with the order less than gamma, you have this assumption, okay? Because the gammas are given explicitly by that. So in fact, you can recognize that this looks like a Taylor expansion of the function Fi around the point y, okay? And x is the generic variable. And okay, if you think of it, and the order is this one, is gamma minus degree of I. So in fact, this is telling you that you have this relation between the components. So the J component for j greater than I must be the j minus ith derivative of fi. Okay, and indeed, so fi has to be of class c gamma minus I, and in fact, for example, for I equal to 0, f0, so the zero component has to be of class c gamma and must satisfy this. So in fact, okay, this is telling you that for the classical model, a model distribution is in fact nothing but indeed the family of derivatives of the zeros component, which has to be a C gamma function. It is indeed equal to the germ that we have discussed in the previous slide. So this also follows again from this property that when the germ is continuous in the two variables, then the reconstruction is just a computation on the diagonal for y equal to x. Okay, I'm sorry. So this is absolutely elementary, but I understand that I'm explaining it in a bit messy way. So again, the message is that for this simple pre-model, model distributions are equal to the collection of derivatives of C gamma functions. Okay, and the reconstruction gives you back the function, the C gamma function. Okay, but the model distribution is potentially more than the function itself. It's the collection of derivatives with respect to the classical monomials. Yeah. Okay, in fact, based on this example, so we can now fix a general pre-model and say that indeed the space of distributions modeled by pi gamma can be described as a collection of generalized derivatives of the reconstruction U with respect to the pre-model. So in rough path, this corresponds to the notion of Gubinelli derivative with respect to the rough path. Okay. So by the way, Massimiliano does not like this to be called the Gubinelli derivative, but okay. So I'm referring to Sebastian Riede's lectures. So that's the same. Okay, that's exactly the same situation. The control path is a collection of one function which was y, and the second function was y prime. So y prime is a generalized derivative of y with respect to the rough path. Okay, and here we are extending this to potentially a much larger class of objects. Okay, you can define semi-norms. So okay, I'm mentioning this especially because I find this fact very amusing. So if you explain to an analyst what you are doing, you can tell him that so he's or she is used to spaces, Sobolev again, Hilbert, how do you say, Bezov, etc., which are fixed. So they are in particular deterministic, while here the Banach or Fréchet, whatever space, where you set your equation depends on an external parameter, the pre-model, which for SDs or SPDs is actually random. So it's a very, I think, beautiful idea that the analytical space where you set your equation actually becomes random, so very much dependent on on an external parameter. Okay, and you see it in particular here. So the gammas will be random, and okay, so if you go back to the definition of the control path, so you recognize that also in that case, so the gamma will be the delta x, and that's also random in the Brownian case, for example. Okay. Now I go to models, which is again not as strong as what Martin would tell you, but it's stronger than the pre-model. So in fact, you have a few additional assumptions on the gamma matrix. Okay, you remember before there was essentially no assumption on gamma, just the re-expansion property with respect to pi, and that was enough to define at least this model space of model distributions. But okay, in fact, you sometimes require a bit more of good behavior. So namely, it is reasonable to require that that gamma I xy is 1, and gamma I j xy so is 0 if alpha I is greater or equal than alpha j and I is different from j. So this is a complicated way to say that there is a triangular structure for the gammas if you order the pi's by their homogeneity. Okay, so in fact, I never remember, but it should be a lower triangular. So you should have ones here, you should have zeros here, and stuff here, if you order the pi i's according to their alpha i's. And plus, you have a sort of control on the diagonal for the gamma ij of this form. So, okay, you see this is when alpha I is less or equal, is greater or equal than alpha j, this is just 0. When alpha I is less than alpha j, this may be non-zero, but on the diagonal, it will be controlled by this quantity. Okay, at least it is quite simple to see that this family satisfies the three properties above. Okay, so we are again extending the classical monomials. Okay, and if you I have a model, then model distributions are particularly well behaved because, so property 1, so the space of model distributions is non-trivial. Okay, so this is a good thing. And for any gamma prime greater than alpha bar, the restricted family okay, what is this saying? This is saying that you have the following good behavior. Suppose that you change your gamma. In particular, you want to decrease it. So this is, I'm sorry. Okay, at the level of the pi, there is at start no gamma. Okay, so you take a gamma prime which is greater than the minimum, and sorry. Yeah, and then you restrict I to the alpha, to the homogeneities which are less than this gamma prime, and it turns out, this is not clear a priori, that the new family is another again a model, and at the level of the model distributions, if you go from gamma to a smaller gamma prime, then you can also reduce, okay, the family of coefficients, and then this is again a model distribution, but with exponent gamma prime and with respect to the restricted model. Okay, so if you think of the classical case, it just means that you truncate your expansion. Okay, instead of stopping at gamma, you stop at gamma prime, and of course you still have a Taylor expansion, just at a lower degree. Okay, this is telling you that you can do the same in this generalized setting, and it's a very useful property when you do computation. Yeah, for the fact that here there's just the proof of point 1. You can see that you have at least one non-trivial model distribution, because if you consider one element of minimal homogeneity, there is at least one, and then in this case you can set gamma. So no, you can see by the assumptions that gamma ij is just the Kronecker symbol, and again, so fjx equal to delta ij will be a model distribution. Okay, so this is really very elementary, but okay, yeah, yes. So this ends the second chapter on definitions on model and model distributions. And I can start with the third chapter. Do you have any question on this? Yes, please. So no, it means that it is not that there is something which is non-zero. Okay, because otherwise you could be discussing just the null vector space, not empty because you have zero, but null vector space. Okay, then we are building a theory for nothing. While in this case, you have at least one non-trivial object. Okay, thanks. Okay, so maybe this part is not very exciting, but it's very important for the rest. Okay, now I come to the third chapter, which is the Schauder estimates for gems. So we discussed reconstruction. This is a second very important tool. Now again, so this lecture and the next are based on work with Luca and Francesco Caravenna, and so we have these lecture notes that I put on my webpage, and also a paper which is going to be finished soon. Okay, and the topic is this convolution with the regularizing integration kernel. So again, I continue with this. We continue with this joke of this title. So we want to reprove these results by Martin, but without using regulative structures. You see that I've not yet defined what a regulative structure is. I'm very proud of it. But again, so in a sense, at some point I will be obliged to, but this in the previous so slide of this kind, we had extracted only the reconstruction theorem, and now we want to extract the multi-level Schauder estimate. And again, we want to present it in a more general and maybe a simpler version. So, okay, what is a regularizing kernel? So this is a bit, okay, just a definition. So we have our dimension D, we have an exponent beta, and a measurable function K, which may be singular actually only at the origin, but then we suppose that this is beta regularizing up to degree m. So we call this beta regularizing up to degree m if the function is of class Cm outside the origin, and we have this upper bound. So for every k with a multi-index with degree less than m, so the kth derivative of capital K, so is bounded by this power of x, okay, times this indicator function, okay, which is practical for the proofs, okay, Okay, maybe we'll mention this later. Okay, so for example, okay, the heat kernel should satisfy this with beta equal to 2. So there are some applications which we have in mind, but okay, we start with this more general setting. So by the way, we can use from time to time this notation for coherent germs. So the space of coherent germs and the space of coherent germs with the homogeneity bound, okay? And again, you see the 2 or 3 exponents which appear. So yeah, again, from now on, we use this kernel, which is singular at the origin. Again, that's the source of some technical problems, but it's singular in a controlled way, and this should be enough to have some non-trivial results in the following. Okay. Yeah. So what are Schauder estimates? So this is a classical result. So I defined the spaces C gamma for negative gamma. So for positive gamma, these are just the classical Hölder spaces. And so for simplicity, let us suppose that gamma and gamma plus beta are not integers. Otherwise, you have to define differently the spaces. So in any case, you have gamma and you have beta, which is positive. You have a regularizing kernel up to degree m, which is greater than gamma plus beta. Again, you suppose this for simplicity. And then the convolution by this kernel defines a continuous linear map from C gamma to C gamma plus beta. Okay, so this is the Schauder estimate. This is the regularizing effect. Okay, you take the convolution of a distribution or a function with k, and you improve the regularity by beta. Okay, this is an important theorem in PDEs, which allows to do non-linear PDEs, then etc. So again, this is only the linear map. Okay. Now, one of the aims, one of the tools, again, in this SPD's business is to lift this operation to germs, in particular to coherent germs. So if you want, you can think again of rough paths. The rough integral, okay, is something which looks like that. So you have what also I defined before. So you want to define, you remember the rough integral was integral from 0 to t of yu dxu, okay? So you can see this as a linear map from control paths to, so again, this will give another control path in the end. So this is a linear operation on control paths. Also, convolution with kernels is supposed to give the same linear operation on coherent germs. But we want this to be compatible with the reconstruction. Okay, so I will be more precise in a second. Okay, let's see. So in fact, one of the steps, technical steps, is with a partition of unity. Yeah, I'm not even sure that this is so crucial for the statements. It's crucial for the proof, but then I won't give the proof. So, so you you decompose your kernel as a series of smooth, say at least globally CM kernels, each supported on an analyse of this kind, and each then satisfying the proper analytical estimates. Okay, So this is again a general fact that you can do that, and then okay, you will prove that the objects are well defined by taking series. In fact, it's the same spirit as for the reconstruction, if you remember. So you decompose your sums in a series over these scales. Okay, you again have your epsilon n sequence which appears. Epsilon n was 2 to the power minus n. Okay, so the singular convolution. So this is what I mentioned in the classical Schauder estimates. So here there is a delicate point. I mentioned it, but then the details are in the lecture notes. So the point is that when you want to take the convolution between a kernel and a distribution, so this is not well defined in general. So formally, you can define this as follows. You would like to apply f to k of x minus dot, okay? But the point is that we said that this is not smooth enough. So this is not, this is singular at x. Besides, it's of class Cm, it's not of class C infinity. So in principle, this is ill-defined, okay? Under suitable condition, this can be defined as a distribution by duality. So you fix a test function psi, and then, so first you take the convolution between psi and k, which now will be well defined as a function of y, and then you want to apply f to this function. But the problem is that this is well defined as a function of y, but it is not necessarily smooth. So again, in general, you cannot hope to define this object for arbitrary f and psi in d prime times d. Okay, so for the special objects that we consider here, this will be possible. There is a little bit of work behind, and again, so I hide this under the carpet, and I refer to the lecture notes if you want to check the details. Yeah. Sorry. Wait a second. So you're right. So psi, because you can write this as psi minus. Yeah, you see, you found a mistake in the end. No, there must be. Wait a second. Well, okay, if it's well defined, then it's even better. But I have to. Okay, sorry. I will come back to this after a moment reflection. So suppose this turns out to be well defined. It's even better. But so maybe Luca, you can help me. Okay, we'll discuss this later. Okay. So yeah. No, I'm going. What have I done? I don't know what happened. Thanks. Yeah, okay. Now this is this is what we are going to do. Again, we have coherent germs. So we said we want to lift the convolution with K on the space of coherent germs. Okay, so in such a way that, so we want to find H in such a way that so this is the reconstruction of H will be the convolution between K and the reconstruction of F. Okay, so this is maybe the most the part where I struggle a bit to explain and to motivate the formula which is going to come. So this is the compatibility with the reconstruction that I was mentioning. Okay, so it's like you want to do this. You, for example, for smooth functions, okay, you have a smooth function. You have its collection of derivatives, and then you want to take the convolution of the smooth function with the kernel, and then have the collection of derivatives of this second object. Okay, and again, of course, the reconstruction of the reconstruction of the second family of derivatives will be exactly the convolution with the reconstruction of the first. So you want this diagram to commute, but so said like that, it's a bit too silly, because a simple solution is just to take this constant germ, which is trivially coherent, and the reconstruction is already the object that you want. But so this is not, in fact, useful for what you do later. Okay, so you want something a bit more complicated than that. Yeah, so one other guess that you could make is the following. So you take hx equal to k convolution fx, but this is not necessarily coherent. So in fact, it needs to be modified, enriched. So one guess is to take that plus possibly a polynomial, really a classical polynomial, again, which will be based, which will depend on this parameter x, but then it's a polynomial in the hidden variable. So in fact, it turns out that this is possible if you define h like that. So these are, again, XL is a new notation for the classical monomials, and the say non-trivial coefficients here are given by this. So this is the reconstruction minus the germ applied to this derivative of the kernel. Okay. Just notice that if gamma plus beta is non-positive, then this polynomial is just supposed to be 0. So this, okay, the theorem that I'm going to state is that this indeed gives a germ which is coherent with the correct exponents, and which commutes in the correct way with the reconstruction. Okay, here I just want to say this. I don't have an intuitive explanation for this formula. So I don't know, Martin, do you have one? So this is, again, so you, Martin, did not work on germs, you worked on model distributions, but so this is the maybe unique extension of your definition to the general class of germs. But still, it is a bit of a mystery to me why this works. So it's okay, another reason to be amazed by all this. So again, I'm sorry, I would like to tell you why this works, but I can't in a heuristic way. So let me state the theorem. So you have again some assumptions on the exponents. So beta positive, alpha less than gamma, gamma non-zero, and actually also alpha plus beta and gamma plus beta non-integers. So suppose that you have a coherent germ and a kernel as we as we mentioned. So I forgot to define R alpha, which was just the smallest integer larger than minus alpha. So now this germ H, which I defined, is indeed well defined. So this is not completely obvious, in particular because here again you are applying a distribution to an object which is not smooth. Okay, so in this case, this is really non-trivial because this is supposed to, in the end, just to give a real number, but you have to prove that this would be well defined. Okay, H is coherent with the correct exponents, and the exponents are the following. So for the alpha, you have this improvement by beta, but you cannot go beyond 0. So if you go beyond 0, you stop at 0, while gamma is increased by beta, as in the classical Schauder estimate. And you have this commutation with the reconstruction, namely the reconstruction of H is the convolution between K and the reconstruction of F. Okay. Sorry, what time is it? Now, so I am repeating what I wrote before. So if I set now K of F equal to H, okay, with H given by the same expression, then you have a well-defined linear operator satisfying, so K maps coherent germs with exponent alpha gamma to coherent germs with exponents alpha plus beta if 0, gamma plus beta, with this commutation property. Okay. Now, there is a nice way to rewrite this, which is the following. So you introduce a new germ, which is Jx, which is f of x minus r of f. Notice this is minus that. So then here what you do is you, okay, you already replace this by minus j. And then here you subtract and sum k plus k convolution rf. And then, in fact, you obtain a fixed distribution plus another germ, which is a linear function of j. Now, the nice thing is that j is exactly the germ which appears in the reconstruction bound. Okay, so this is very, very useful because we know that by the reconstruction bound, this has homogeneity gamma. So we didn't assume any homogeneity property for F, any homogeneity bound for F, but we have, by the reconstruction theorem, automatically a homogeneity gamma for J. And then, since this is just a constant distribution, we can work on L, which is a function of J. And this is a nice remark. Now, the sketch of the proof is the following. So you prove that L is coherent with the correct exponents, and that L has homogeneity bound with exponent gamma plus beta. In other words, you show that L belongs to this space. And again, I stress that we did not assume homogeneity of F. Indeed, in general, H will not be homogeneous. It's just a property of L, but not necessarily of the fixed distribution you have here. Okay, so the first property says that you have a reconstruction for L. So coherence implies existence of a reconstruction at level gamma plus beta. And then the fact that L has homogeneity bound with exponent gamma plus beta implies that 0 is a reconstruction for L. Okay, maybe I can just write this. So you're assuming, so you're proving that Lx computed over a text function of this form, so is bounded by epsilon n to the gamma plus beta. Yeah, and so here, okay, if I write this like that, this is saying that 0 is a reconstruction of L with, say, gamma equal to gamma plus beta. And then, okay, if you sum this fixed distribution, this is telling you that the fixed distribution is a gamma plus beta reconstruction of H. So, namely, this proves the correct how do you say, commutation with the reconstruction. Okay. So this is maybe, yeah, this is a bit more technical maybe than the reconstruction. So let me mention that in the reconstruction proof we had the two terms. You remember this decomposition with J prime and J double prime. So here we have a similar decomposition, but there are 5 terms for the coherence and 3 terms for the homogeneity bound. They are of the same nature, okay? It's always the same kind of, everything is based on coherence, on the reconstruction bound, and, but okay, I thought that it would be a bit heavy to present this on the slides. Okay, again, what I find interesting is that this motivates the next step, which is the true multi-level Schauder estimates, which means the same result, but at the level of the model distributions. Okay, so let me draw another diagram. So you have here the coherent germs. So you have this space G of alpha gamma, and so this operator K. Okay, it's more calligraphic K, which maps into G of what did I write? So it was alpha bar. I forgot. What did I write? It was, well, okay, let's stay just at the level of, yeah, it was gamma plus beta. No. Okay, let's just stay at the level of coherent germs without the homogeneity bound. So it was alpha plus beta inf 0, gamma plus beta. Okay. And actually here below you have this okay, these model distributions D gamma, which map into coherent germs. And on this side, yeah, this will be the point of the next chapter. So, yeah, at this level, I can put here a question mark, because it's not clear what the model will be on the right. But okay, we will show that there exists a model. So this will be replaced by an object, okay, that we will construct. And, okay, in such a way that this also gets mapped into the correct space of coherent germs. And then, of course, K, we don't know whether this does map this space in that space, okay? Or if you want, whether there is a map which then makes the diagram commutative. So this is the real multi-level Schauder estimate. Okay, it is Schauder in the sense that you always have this gain in regularity, but it is multi-level because, in fact, this tells you more. This is really controlling every coefficient of the model distribution F and giving, say, stronger estimate on these separate coefficients. Okay, so again, for the equation, it is the lower level which is relevant. So the upper level, what I presented today, is not yet at least used in application. So again, it is a map on germs which form a very big space, maybe too big. Still the state, so the theorem is nice and the proof is interesting. By the way, I'm not going to give the proofs, but in fact the two proofs are quite different. So this is also somewhat puzzling because one would expect the two theorems to be very, very close to each other, but so the two informations are actually quite different. So here you act on a smaller space, but you get more information. Here you get on a larger space, but you get a weaker information. Okay, so we try to think of this, but we did not see really how to reduce one result to the other. So maybe it's really not even possible. So this will be the content of the next lecture. So the lower level, the action of this convolution on the space of model distributions, which is announced here, but again, so the lecture notes are already prepared, but the slides are not yet. So again, I can stop here. Thank you.
Questions, comments? Thanks for the talk. Does this, the Schauder estimates also work for all the scalings? Because for the heat equation, for instance, we would want parabolic.
Yes, yes, okay. Yes. No, that's again just for ease of presentation, but the scalings are an easy adaptation.
Okay, thanks.
Thanks.
Anyone? Oh, if not, let's thank you again.
Thank you.
Do you have a break for? Huh? So we return at 11, right?
pronounce your name? Luca. Oops.
My name is
I was not sure if the X at the end was
yeah, it is,
pronounced.
but most people don't.
Lorenzo student?
Yes.
PhD student?
Yeah.
Nice. Okay. It seems to be a, well, I would guess it's a practice. Makes an effort. Everyone, this is the first exercise section on regularity structures with Luca Brooks.
Thank you very much for the introduction, and thanks to the organizer for organizing this this conference. Okay, so already in these slides there are a few lies. The first lie is that there will be no exercise in these exercise sessions. In fact, I will. With Lorenzo, we thought it would be more interesting from a pedagogical point of view if I rather guide you through an example of equation and do, I mean, all of the details that I can do. And the second lie is that today I will not really talk about regularity structures. I will try to do the classical case and try to explain why the classical case doesn't work in all dimensions and how to heuristically introduce regularity structures. Okay. So what are the comments for this? Is it okay? So this is the equation that we will consider during all these exercise sessions. So we consider a Gaussian white noise, and we consider as well two parameters alpha and beta, and we'll be interested in this equation. So minus Laplacian of phi equals alpha plus beta phi times xi in RD. And in fact, we'll be interested in the case d equals 1 and d equals 2. And okay, so the subtlety with this kind of equation is that xi, the white noise, is a very irregular distribution, and it is more regular when d increases. And so the product phi times xi might not be defined in general. So this is why this equation is interesting. So in these exercise sessions, I will consider only the case d equals 1 and d equals 2. So today I will present a few of the tools that are used in discussing the case of the dimension 1. So in the dimension 1, in fact, the product psi times phi is well defined. And so we can close the PKR fixed point iteration. While in dimension 2, this product will not be defined anymore. So we'll have to actually use regularity structures to perform a renormalization. Okay. Maybe just a comment. So I don't know of any physical usefulness for this equation. So in the literature, there have been a lot of equations like KPZ or parabolic Anderson model and so on, which have been studied for reasons that were introduced by physics. Here, the equation is just some kind of toy equation. I would say a pretext to illustrate on a simple case some of the analytic aspects and some of the probabilistic aspects of regularity structures. The advantage of this equation is that in the dimension 2, there are only a few terms that will appear in the regularity structure. So we can, I will be able to present to you explicit calculations for the models and the renormalization and everything. If you wanted to consider more complicated equations, you would have needed to introduce some algebra. But okay, this would also add a further layer of abstractness in this situation. So we will not discuss the algebraic aspects in this session. Okay. So today is the first session. Okay, a few remarks on the equation. Okay, please interrupt at any time if you have any questions, by the way. So the equation minus delta phi equals alpha plus beta phi times psi is an elliptic equation, meaning there's no time in it. And so this brings some subtleties, which I will either discuss or put under the carpet. The first maybe subtlety is that for parabolic equations, for instance, if you want to solve the equation as a fixed point equation, you need to adjust the time because the constant in the fixed point estimates will depend on the time interval that you're considering. So in the parabolic equations, you can always fix a time interval sufficiently small so that the constant it becomes smaller than 1. Here you don't have this smallness. So the smallness will come from the two parameters that we have introduced in the equation, the alpha and the beta. In fact, only on the beta. Another remark is that for boundedness reasons, we might want to work on compact or compact subspace of RD or the torus, for instance, in order to benefit from the boundedness properties. So as we will see, so I will define precisely what I mean by white noise. And we will see that the regularity decreases when the dimension increases. So you expect the equation to be more and more difficult to discuss. And maybe a last remark is that, okay, with elliptic equations, there are a lot of subtleties around questions of uniqueness and boundary conditions and everything. So we'll just be blind to these technical difficulties and put them under the carpet because okay, they will not be very enlightening. And also, I'm not sure that I can do all of them. Okay. So in fact, as is very useful in this kind of situations, we will not discuss the equation as written in here, but we will replace it by a mild formulation, meaning we will rewrite this as a fixed point where, okay, obviously, okay, I destroyed everything. Oh, is this? Okay, perfect, thank you. So in some sense, we compose both sides by the inverse of the Laplacian, but of course the Laplacian is not inversible. So what we do is we convolve by the Green's kernel. So here the fundamental solution of the Laplacian, which is explicit in dimension 1 and in dimension 2. Okay. So really the equation that we will consider is this one. And the question, of course, as in all these kind of questions, is we want to set a fixed point for this equation. So the first question is, in which space do we want to do this? And in dimension 1, the spaces that are useful for this are the Hölder spaces. So, okay, the classically Hölder functions for exponents alpha between 0 and 1. You've seen quite a few times, I think, during the past weeks, that they are defined like this. So a function is Hölder if it satisfies this kind of estimates. Okay, so this kind of this estimates. What when alpha is greater than 1, you know that it implies that the function is constant. So when alpha is greater than 1, you have to adapt the definition by subtracting a general Taylor expansion. Yes? What do you mean? Yeah? Here? No. Here I really mean, for instance, if it's 1.7, you subtract the phi and phi 1 of x, and you ask for it to be smaller than 1 minus x to the power 1.7, really. Yeah. Okay. So this is the general definition of Hölder functions for positive exponents. And of course, as you've seen in Lorenzo's presentation, we can generalize this, in fact, for distributions. And the way to do this is, okay, if you consider again the case of alpha between 0 and 1, and you apply phi as a distribution against any test function centered at x and rescale at scale lambda. So I use the same notation as Lorenzo here to denote, by this I denote the test function eta centered at x and rescale at scale lambda. So if you express what this means, you will obtain this integral. And since you have an explicit expression for this, you can just do the usual change of variable in this integral, and you obtain this integral. So the integral of phi against eta. So this is a big O of 1. But if, on the other hand, you furthermore impose that the test function eta should be of integral 0, then you can subtract this term, which equals 0. And you can exploit here the assumption of being Hölder to obtain that this is a big O of lambda to the power alpha. So in general, as we've seen, we need to subtract Taylor expansions. So a notation which is useful to introduce is this one. So you consider the test functions with support in 0, 1, with CR norm bounded at 1, and which furthermore annihilates the polynomials when you test against them up to degree alpha. And so this allows you to construct a family of seminorms. So this really is the same thing as I wrote in the previous slide. So f tested against eta for test functions which don't necessarily annihilate polynomials should be bounded by a constant. And if you assume that you annihilate a few polynomials, for instance, then phi of eta x lambda should be bounded by lambda to the power alpha. So this is interesting because this definition can also be written when alpha is negative. When alpha is negative, this constraint disappears. Okay, and so this we retrieve the definition of negative Hölder spaces from Lorenzo's presentation. Okay, so this gives really for all exponents alpha in R a fresh space, a complete metrizable space, metrized by a family of seminorms here. And one interesting exercise to do if you want to make sure that you've understood this definition properly is to verify that if you consider an actual distribution phi which satisfies the Hölder property with this definition, you can prove that it actually is a function which satisfies the Hölder definition of the previous slide. Okay. So the Hölder spaces are quite interesting because they allow you to talk about the regularity of a distribution or a function. And so there are naturally a lot of questions of stability that can be asked about Hölder spaces. So for instance, okay, the first question is, in the equation that I want to discuss, there is this Gaussian white noise. So the first question is exactly what do I mean by Gaussian white noise? And how can I quantify Hölder regularity? It's the continuation of the Brownian motion course of last week. What is a Brownian motion and what is its regularity? So you can answer these questions. And the second and third point have also been mentioned by Lorenzo's course, so I will just not insist on them. But there are properties of stability by multiplication of the Euler functions, and there are properties of stability by convolution. Okay, so I will go back to this later, and I want to start by the first question. So, okay, this is a probability school, so we felt like it's quite important to talk about a bit of probability. So I will now define white noise, Gaussian white noise, and talk about its Hölder regularity. Okay, so there's a very general definition where we consider any general Hilbert space, and we define Gaussian white noise on this Hilbert space to be any linear isometry between H and L2 of omega Fp, where omega Fp is any probability space. And isometry, so here there is a natural Hilbert structure on L2 omega Fp. And there's this further condition that for all H in this Hilbert space, psi of H should be a real valued centered Gaussian variable. Okay. Okay, a bit more explicitly, the isometry property means that for any elements H1 and H2 in the Hilbert space, the expectation of psi of H1, psi of H2 should be just the scalar product between H1 and H2. And in particular, since psi of H is a real valued centered Gaussian variable, its law is defined by its variance, aka H square, the norm L2 of H square, the norm of in H of H square. Okay. So just as for the Brownian motion, these constraints define a sufficiently consistent family of marginals. And so there is the very general Kolmogorov's extension theorem, which says that okay, you can realize such a Gaussian white noise. Okay. And so in the case that we'll be interested, for us, H will be in fact equal to L2 of RD. Okay. And so you see that okay, Gaussian white noise exists on L2 of RD by Kolmogorov extensions theorem. And no psi is something that eats functions. So for instance, any test function is a function in L2. So it eats test functions and it gives a random variable. So the natural question that comes is, as a distribution, does psi admit Hölder regularity? Okay. Okay, so it's a question that I wrote here. And just as for the Brownian motion, there's a very general Kolmogorov continuity theorem for the spaces of distributions, which tells you that if you consider X from L2 of RD to L2 of omega Fp to be okay, continuous in the sense of the Hilbert norm of both of those spaces, if you furthermore assume that you have this estimate, so this is really similar to the estimate of Kolmogorov's continuity theorem for functions. So the estimate is that the expectation of psi tested against test functions centered at X and with scale okay, 2 minus k, at the power p, this should be bounded by a constant time 2 to the power minus k alpha p. So this is really asking you know, to test something on a scale 2 minus k. The expectation of this at the power p should be bounded by the scale to some power. Okay. And then the consequence of the theorem is that there exists another function x tilde, which coincides with x almost surely. So it is a modification of x. And the other consequence is that for all, not only almost surely, but always, and for all exponents alpha prime smaller than alpha minus d over p, the random variable x tilde is in fact a distribution with Hölder exponent alpha prime. Okay, so this is really an analog of the Kolmogorov's continuity theorem for functions. And in fact, the proof even is analogous. So the proof of Kolmogorov's continuity theorem for functions uses you know, this idea of looking at what happens on the dyadic scales. And here is the same, but you have to use a bit more complicated dyadic decomposition, such as either you use wavelet decompositions, or you can prove this result using more elementary little loopally decompositions, but the proof is a bit longer. Okay. But I will not enter in the details of this. Okay, let us just check that the test function, the white noise, Gaussian white noise psi satisfies these conditions for alpha equals minus d/2. So if you consider psi Gaussian white noise, you can in fact really easily estimate this, because psi of eta x to the power 2 minus k, this is just a Gaussian random variable. So for Gaussian random variables, you have the properties of equivalence of moments, which says that the pth moment can be just bounded by the second moment, the variance. So you can bound by here just the variance of psi of eta x to the power 2 minus k, and by the property of isometry of white noise, then this is just the L2 norm of this function eta at scale 2 minus k. So to explicitly compute this L2 norm, you can just do the calculation. So this is by definition the integral of eta x 2 minus k against itself, and because this is explicit, you can just write explicitly what it means. So this is what I done in the second line. This is a 2 kd eta of 2k 1 y minus x, and same here. And so what happens here is that you do the change of variable u equals 2 to the power k y minus x. So there is one of the 2 to the power kd that is swallowed by the change of infinitesimals, and you remain with this 2 to the power kd times something. So the conclusion is that you have really estimated the expectation that you wanted to estimate, and you obtain a constant time 2 to the power k alpha p, where alpha is minus p/2. Okay. So the conclusion of this is that the Gaussian white noise, it exists, and any one of them has a modification which belongs to c minus d/2 minus kappa for any kappa strictly positive. Okay. Maybe a small remark is that here the Gaussianity with the assumption of Gaussianity of the white noise, we've used it only in the previous slide, so only in the form of the fact that the Gaussian moments are bounded by the variance. And in fact, we can exploit the Gaussianity in a slightly smarter way to prove that the Gaussian white noise has a modification which belongs to a bit more general base of space, but with really the exponent minus d/2. Okay. So here we cannot attain the exponent minus d/2, but if you are willing to work in the base of scale, you can attain the exponent minus d/2, but you have to restrain yourself to finite integrability assumptions. And okay, you have the base of, okay, I don't want to develop what base of spaces are, but they have the nice embeddings theorems. And one of them says that this base of space is included in the space C minus d/2 minus d/p. So this is really slightly stronger than the proposition that I wrote here. Okay. So now we're done with the probabilistic part of today. And okay, let's try to do the pk iteration of the equation that we consider in dimension 1. So recall that we consider this equation, and we want to solve this equation because C alpha has all these nice properties of stability and everything. We want to solve it in the Hölder space. So in the dimension 1, yeah, recall that we asked a few questions about the stability properties of Hölder spaces. So now we'll just answer them without much detail. So the Gaussian white noise, we've seen that it belongs to the Hölder spaces of regularity minus d/2 minus kappa for any kappa strictly positive. And for d equals 1, so you can particularize this, and it's minus 1 half minus kappa. Okay. The result of multiplication is what Lorenzo called the Young multiplication in his lecture. And so it says that if you consider, let's say, a very irregular distribution, you can multiply it, but only by a very regular function. And so the precise theorem says that this product between C alpha and C beta is canonically well defined if and only if alpha plus beta is strictly positive. Okay, and just as in the classical case, the regularity of the product is just the minimum of the regularities of the two functions. Okay, and there are even continuity bounds, which I wrote here. So, okay. Yeah. Okay, and for the convolution, also Lorenzo mentioned it in his lecture. So the intuition behind this is that convolution by k is like inverting the Laplacian. And the Laplacian reduces regularity by 2 because you differentiate twice. And so it makes sense that the convolution should increase regularity by 2. Okay. So the precise result is that for any alpha real, then the convolution with k brings you from C alpha to C alpha plus 2, and there are even continuity bounds, which I wrote here. Okay, maybe just a small comment is that in Lorenzo's lecture, he singled out the case where alpha is an integer. He said it didn't work for integers. Here, the reason why it worked for integers is the choice that we made for the spaces C alpha, which are slightly different at the integers point than what Lorenzo introduced. Okay. Okay, so now we try, let's try to actually perform the PK iteration. So what we mean by PK iteration is just we take any function at the beginning, and then we iteratively apply the right-hand side of the equation to this. So since psi is in, okay, so the first term of the PK iteration is just, we just set it to be 0. So this is the C infinity functions until there everything is good. And then what we do is we apply the right-hand side of our equation to phi 0. So phi 1 will be k convolved with alpha plus beta phi 0 times psi. And so since phi 0, we chose it to be 0, then, okay, it simplifies to alpha k convolved with psi. So psi is in C minus 1/2 minus kappa. And convolution by psi improves regularity by adding 2. So we end up in C 3/2 minus kappa. Okay. Now let us do it again. So the second term of our PK iteration is just applying the right-hand side of our equation to the first term of the PK iteration. So we do k convolved with alpha plus beta phi 1 times psi. Okay. So now we want to investigate in which space this belongs. So psi belongs to C minus 1/2 minus kappa. Phi 1, we've seen that is in 3/2 minus kappa. So the sum of the exponent is strictly positive. It's 1 minus kappa. And so we are justified in doing the Young multiplication here. And the term inside the convolution here will inherit the regularity of the lowest regularity of the two terms of the product, which is psi. So this parenthesis has regularity minus 1 minus kappa, which is the regularity of psi. And so when you convolve by k, you end up again in C 3/2 minus kappa. Okay. So this suggests that we can, in fact, close the loop in dimension 1. And so, yeah, this is true. So the iteration map, which we define here, turns out to be well defined by the calculations that I've mentioned in the previous slides. And by combining all the continuity estimates that I've shown you in the previous slides, you obtain even that P of phi 1 minus P of phi 2 in the correct corresponding norm. This is bounded by phi 1 minus phi 2 in the correct norm times a prefactor, which is a constant, times the coefficient beta of the that we introduce in our equation, which we will need to adapt to have the contraction. And then there is this norm of the noise over compact k. So here, yeah, there's a small subtlety that the Lipschitz constant of this map depends on the compact k via the norm of the noise. So this is one of the subtleties of elliptic equations. So here, there are possible ways to work around this. Either we construct a solution on bounded parts of the space, for instance, on the torus, and this will just be bounded by a constant, and we can fix beta to be small enough so that this is smaller than 1. Another solution would be to work with weighted Hall spaces. So we could add weights to Hall spaces in order to avoid this problem of having the knob of the noise here. Okay, but I will not discuss how to do it. So if we admit that this is not a problem, when we set beta to be small enough, then our equation is well defined because this becomes a contraction. Okay. Maybe just another small remark is that because this is a random quantity, either one choose beta to be a random variable, so we have an equation where the parameter beta is random. This allows to construct a solution almost surely. Or if we fix beta in a deterministic way, so the function, so this will be a fixed point only with positive probability, not necessarily one. Okay. Okay. So I hope that I conveyed to you that in dimension 1, at least, the Picard iteration works as intended. And let's see that it doesn't work in dimension 2 anymore. So in dimension 2, the only thing that changes is that the noise is no longer in C minus 1/2 minus kappa, it's now in C minus 1 minus kappa. And so we do the Picard iteration exactly in the same way. So phi 0, we set it to be 0. Phi 1, we set it to be the right-hand side of the equation applied to phi 0. So this is still alpha k convolved with psi. And now this, because psi is in C minus 1 minus kappa, but k is still 2 regularizing. So this is in C1 minus kappa, 1 being minus 1 plus 2. Okay, and let's try to pursue the Picard iteration. So at the second term is k convolved with alpha plus beta phi 1 times psi. And the problem is that phi 1 times psi now is an ill-defined product because phi 1 is in C1 minus kappa, psi is in C minus 1 minus kappa. And to check whether this is a canonical or ill-defined product, one has to check is the sign of the sum of the exponents. And here, 1 minus kappa plus minus 1 minus kappa, it becomes a negative, strictly negative. So there is no canonical product between those two spaces, and so we cannot immediately close the loop. Okay. So at this point, there is there have been some techniques that have been introduced to deal with this kind of situations, even before regularity structures. And one such technique is the so-called Proto-Bush Trick, which here would consist in we consider a new function, which is just phi minus the first term of the Picard iteration. And the idea would be that maybe this phi should have should be better behaved than phi. Yeah. So the interpretation is that maybe if we remove the term of worst regularity in the Picard iteration, then maybe we can write a fixed point on psi and be able to still close the loop. Okay. So there is a fixed point on phi. So we can just write another fixed point on psi. So psi is phi minus phi 1. And phi is just k convolved with alpha plus beta phi times psi. And phi 1 is just the same, but here it's 0. So the first term of the Picard iteration, as previously, is alpha k convolved with psi. And so there's a simplification which appears here. And so this psi is just beta k convolved with phi psi. And so when we replace phi by phi 1 plus psi, we obtain a fixed point on phi, where phi should be beta k convolved with phi 1 psi plus beta k convolved with psi psi. Okay, so there is again maybe a subtlety here in the sense that I just told you that this product couldn't be canonically well defined. So the difficulty in the previous Picard iteration is that we wanted the product to be well defined all the time. Okay, we wanted the Picard iteration to be able to make the Picard iteration in general. But here, phi 1 is just alpha k convolved with psi. So there is a probabilistic structure to this phi 1. And so there are techniques using, for instance, weak products that allow us to give a meaning to this product, still in C minus 1 minus kappa, using some probabilistic techniques. So I will not enter in the detail of this right now, but let us assume that we can, in fact, multiply phi1 with psi in a somehow canonical manner, and try to see if we can really close the fixed point iteration for psi. Okay. So again, we chose psi 0 to be 0. Psi 1 should be the fixed point, the equation for psi applied to psi 0. So if you remember, the equation for psi is this. So when I apply it to psi equals 0, then I will just get beta k control with phi 1 psi. And so this is okay, we assume that we were able to construct this product in C minus 1 minus kappa, which is the lowest regularity of psi and phi 1. And so by the regularizing properties of K, this would belong in C1 minus kappa. Okay. And once again, we are in trouble because, this product phi 1 times psi, know that phi 1 is 1 minus kappa holder, psi is still minus 1 minus kappa holder, so this is still canonically ill-defined. There is still no canonical meaning in general, so we cannot close the loop of the PK iteration. Okay, so now maybe the first idea would be, okay, it didn't work because I don't know, I just subtract the first term of the PK iteration. Maybe I should subtract more. Maybe I should iterate this technique and try to subtract the first term of the PK iteration of psi and try to do it again and again and again. And the problem is that this does not work because at the first step, here you see that we only obtain a function of regularity 1 minus kappa, which was the same regularity that we obtained for the PK iteration of phi. So if you try to iterate this technique, then every time you iterate it, at the first iteration, you will obtain something that is 1 minus kappa holder. And so this makes that the second iteration will not be well defined. So we cannot really iterate this this technique. And so in a sense, this means that we cannot really close the PK iteration in holder spaces. So we need to do something more complicated. And maybe one heuristic remark that is in some sense a bit interesting here is that if you consider, for instance, even alpha and beta holder functions for alpha between 0 and 1 and beta between 0 and 1, then the regularity of the product, the holder regularity of the product, will be the minimum of the regularities of f and j. But if you consider this term, then of course, then this is bounded by 1 minus x to the power alpha, and then this is bounded by y minus x to the power beta. And so you obtain the sum of the regularities on the right-hand side. And the sum of the regularities here, it can improve. It is typically bigger than just the minimum. So the interpretation is that maybe if we stop considering functions, but if we start considering germs, such as this, that is local approximations of functions, then, and if we, instead of looking at the regularity here, we start looking at the homogeneity of the germ, then the PK iteration will look a bit better and we'll be able to substantially close it. So the heuristic conclusion of this remark is that if instead of working with functions, we wanted rather to work in germs, then the PK iteration would be made possible. Okay, but of course this is a really heuristic remark, and we need to really set up the whole theory before this becomes rigorous. Okay. Any questions so far? No. Okay. So okay, I think I went a bit faster than I expected to, so maybe we'll be able to to start talking about germs. So let us remind you a bit of what Lorenzo did yesterday and this morning. What is a germ? A germ is just a family of distributions indexed by the space, RD, and we interpret it as a family of local approximations. Okay. So what this means for the equation that we consider is that instead of trying to solve it for Hölder distributions or Hölder functions, we'll try to solve it at the level of family of local approximations of a nice solution to find. And the basic example, which Lorenzo already mentioned, is the Taylor germ, the germ of Taylor, the natural Taylor expansion of a function f. So if you consider a function f, you can denote t of f at point x to be the Taylor expansion, really, of f at x. Okay. So Lorenzo has isolated two interesting properties of germs. So we said that a germ is alpha gamma coherent if it satisfies this estimate. So fy minus fx tested at test functions phi centered at x and with scale lambda can be bounded by this quantity. So it tells you at the different scale y minus x and lambda how close you should be. Okay. And the second property is the property of homogeneity, which is maybe a bit easier to understand. We said that the germ is say alpha bar homogeneous if fx tested at phi x lambda is bounded by lambda to the power alpha bar. So this, for instance, so this tests how close fx. I mean, it says how fx should diverge in some sense when we try to apply it to a Dirac. And the calculation that Lorenzo did, I think, yesterday, is that if you consider a gamma Hölder function with gamma positive, then its Taylor germ will be a zero gamma coherent germ. This is the calculation that he did yesterday, and also it is zero homogeneous. It is bounded. Okay. And so, of course, when you have germs, you need to know if it can be mapped to actual distributions. So if given a germ, you can find a canonical distribution which should be associated with it. And the result of reconstruction, which Lorenzo already mentioned yesterday, is that if a germ is alpha coherent for some gamma strictly positive, then there exists a unique distribution, which we call its reconstruction, such that the germ R of f minus fx is homogeneous of degree gamma. So this means that R of f minus fx, especially if gamma is strictly positive, it means that R of f minus fx should be really close to zero. And so in some sense, R of f is really well approximated by the approximation fx. Okay. And again, if we come back to the example of Taylor germs, if you consider a gamma Hölder function, then the reconstruction of its Taylor germ is just f. And in fact, there is this useful particular case that was mentioned this morning, is that if the map xy to fx of y is a continuous map, then by definition of the reconstruction, we can actually express the reconstruction explicitly by just fx of x. Okay, but of course, the advantage of the reconstruction theorem is that it works even for distributions. So there's a continuity result in the sense that if you approximate a distribution by some functions, then this will be your reconstruction at every time, but the limit, you won't have such a formula. Okay. So once again, the heuristic suggested that we should perform a fixed point argument at the level of germs. And the question now is that, can one perform the operations that appear in the fixed point equation? Can I perform them at the level of germs in a way that is consistent with the reconstruction? So for the convolution with the kernel K, this is what was discussed by Lorenzo this morning. And the result is that if you consider any alpha gamma coherent germ, then if you convolve f by k and subtract this nice, it's just a polynomial germ, So if you take the pointwise convolution and you subtract sufficiently nice polynomial, then you will indeed increase the coherence exponent by 2, and you will commute with the construction. So this is the first part of what we want to do here. And so, okay, I stated the result for the fundamental solution of the Laplacian, because the Laplacian is this will be 2 regularizing, but as Lorenzo explains, there is a general classes of regularizing kernel for not only by 2, but maybe by other regularization constants. Okay. And so the advantages of the reconstruction theorem and of this Schauder estimate is that they work really at the level of distributions. The problem, of course, is the product, once again. So there's no canonical way of multiplying 2 germs. But however, if you consider, of course, 2 continuous germs, you can just multiply it pointwise. And then by the small formula that I wrote just a few slides before, if the reconstruction is applicable, then the reconstruction of this product will be just the product of the reconstructions. But of course, we're not interested in continuous functions, because I mean, in the PK iteration, there are always distributions that appear. So the question is, what is the stability of this kind of operation when we make the functions go to distributions? Okay. So you see that I have 15 minutes of advance, and okay, I'm already done with this first session, so maybe I can start with the beginning of the second one. So yeah, because when I prepared these exercise sessions, I thought that I would have 3 hours in total, 2 times 1.5 hours. So there is still quite a lot of material. Maybe it's not a bad idea if I start to continue now for maybe 10 minutes. And unless there is some questions already for. Okay. Okay. No questions? All right. So let's recall the situation. So we have this fixed point equation. So, okay, what we always do in regulative structures is that we modify the noise. So we approximate it in this way. So what we do is we take the test function, which integrates to 1, and we convolve the noise with the test function will scale epsilon. So this is a smooth approximation of psi. Okay. And so what we do is we replace psi by psi epsilon in this equation, and we want to know what happens when epsilon goes to 0. And rather than doing it directly at the level of Hölder functions, like we tried to do, let us try to do it at the level of germs. So we replace this equation by the corresponding equation, where we replace the convolution by k by this map k. And yeah, we replace the product by the pointwise product, as I explained. And so if we are able to solve this fixed point equation at the level of germs, because everything is smooth here, everything is continuous. If you can apply the reconstruction to this to the fixed point f epsilon, then you will end up satisfying the original equation, just because everything is stable. Okay. Yes. Yes, this is a germ. This is a family of local approximation. There should be an x here. Yeah, x. There should be x every time, because everything is indexed by space. No? Yeah. Yeah, xi does not depend on x, but f does depend on x. But we can interpret xi as a germ by postulating that it should be constant. I mean, on every point we give xi. Okay. So we have this equation, and we want to find a nice, of course, as always, complete metric space of germs where we would be able to set up the fixed point. And so if you try, again, as before, to do the pk iteration, so we would set maybe f epsilon 0 to be 0, the constant germ equal to 0, and then apply the right-hand side of this equation to f0 and so on and so on. So the first term of our pk iteration should be k evaluated to alpha plus beta f at 0, f, the first term of the pk iteration, times psi epsilon at x. So here I really put the x. And so this is 0, it cancels. And okay, the convolution map of the constant germ psi epsilon. So you remember that the convolution map, it's K-convol with the germ minus Taylor remainder. And here the Taylor remainder vanishes because psi epsilon is just constant everywhere. Okay, so it is equal to its reconstruction. So the first term of the pk iteration is just alpha K-convol with psi epsilon. And so what we can do is express this as a linear combination of homogeneous germs. So the first by subtracting the suitable Taylor expansion, and the second is just 1. Okay, so we can rewrite the first term of the pk iteration as alpha times this germ, which we can check to satisfy the homogeneity property with exponent 1 minus kappa. This is because we subtracted the suitable Taylor expansion, plus a function of x times just the germ equals to 1, which is 0 homogeneous. And so if you try to pursue this computation, you will just observe that the germs that will appear in the pk iteration is just linear combination of fi of x times germs pi I epsilon of x. So here, this would be a f of x, and this would be a pi epsilon of x. Okay. And same, this would be a f of x, and this would be a pi epsilon of x. And you can try to do the actual iteration, and there are, and so you can try to write as well the germs that appear in the different steps of the pk iteration. So of course there are, because the pk iteration will become bigger and bigger and bigger, we need to truncate at some point, and I truncated at homogeneity 1. So yeah, okay. So this is really what the model would be in the context of regularity structures. Maybe some remarks. So the term of lowest homogeneity is just the noise. So this is okay. There is no x here because this is just a constant. Okay. There are also the polynomials that appear. So 1, the monomials here. So we're in 2 dimensions, so we have to be careful that there is 2 monomials here, x and y, x1 and x2. So this convolution terms is the one that we saw appear in the previous slides, and then there are the different products and. So every time you do the pk iteration, you have products that appear and you have convolutions that appear. So if you list them, you obtain here this product between the germ that is here and the germ that is here. And here it is the product of the noise and the first monomial. And okay, if you wanted to pursue the list, you would find maybe more longer to write and a bit more complicated terms in the model. Okay. Okay. So any questions on this? Yeah, exactly. So the pi. So the pi is the one that appear are those that are in the lines here. Okay. So for instance, this one appeared here. Okay. And the one that is here is just the first monomial. and it appears here. Okay, and since every time you have either to multiply germs or you have to take the convolution, okay, you also have to subtract the suitable Taylor expansion at each time, because you want to have a nice homogeneity property. So the reason why I subtracted the K-control with psi epsilon of x here is that this germ as written as really homogeneity 1 minus kappa, while just K convolved with psi epsilon is just a function, so it I mean, it will have a regularity homogeneity 0. Okay. Okay. So what I try to justify is that when we do the PK iteration, there are really this model distribution that will appear in some sense. That the germs that will appear will be of this linear combination, and the pi x epsilon naturally appear one by one. Okay. Yes. Hmm. Hmm. Sorry? Yes, I will. In fact, I define them in the slide just after. Oh, okay. I don't know what. Okay. Yeah. So there are quite useful symbolic notations. Okay. So the dot is used to represent the noise. And so in situations where there are more noises, you can number them, for instance. The bar represents a convolution, so here with the kernel K, and once again, if you have several kernels, you can also number them. And there's this some sort of symbolic multiplication. So where the unit element is the monomial 1, and for instance, the multiplication of the noise and the convolution of the noise will denote by this. Okay. So if we come back, yeah, we observe that the blue dot is used for the noise. This is the convolution of the noise, where we subtracted the suitable Taylor remainder. And this is the multiplication of okay, so we call this the lollipop. This is the multiplication of the lollipop on the noise. And this is also the multiplication of the noise with the first monomial. Okay. And yeah, so maybe a last comment is that so the procedure that I've done here, I did it by hand, but okay, hopefully you can convince yourself that if I give you any fixed point equation with kernels and multiplications, then if you consider the right algebraic formulation, you can also do this. So this is the content of the algebraic part of regularity structure. This can be made systematic if we consider a general equation. Okay. And so yeah, the advantage of these tree notations is that they allow to really simplify the expression. For instance, if I consider this big model distribution, say, with the psi epsilon plus 3 times x times k convolved with this. So either I can write it in the form of a germ explicitly here, or I can write it as with the symbolic notation as pi x epsilon of just the blue dot plus 3 times x times this tree evaluated at y. Okay. Okay. So yeah, I think I think it's time now. So thank you very much. So I will continue this on Thursday.
So hello everyone, welcome back. So it's my pleasure to continue to announce the second lecture of Professor Martin Heyer. Martin, please.
Okay, thanks. So let me just try to do a very quick recap of what we've seen yesterday. So remember, I sort of tried to explain this whole setup, which now from now on we're always actually going to simplify things. So this bundle P, we're actually always going to choose it to be just the d-dimensional torus times the Lie group G. You know, you can, in principle, you could do a lot of more complicated situations, but it's going to be, in any case, it's certainly going to be very convenient that the base space is the torus. And so then, given such a principal bundle, we've seen this notion of equivariant connection, which we've essentially identified with one forms that take values in the Lie algebra of G, which we call sort of Gothic G. So that's the Lie algebra of the structure group G. And so the field, if you want the Young-Mills field, was A, which was an equivariant connection on P, which we saw is really a one form, and so it means that we can really view it, right? So if this is just the torus, we can really view it as just functions AI that go from the torus into the Lie algebra, from I going from 1 to D, okay? So now that's a one form, which of course, you know, if you're on the torus, everything is flat, and so one forms and vectors is basically the same, or at least there's a canonical way of switching between the two. And then, given such a connection, we've introduced this notion of curvature, which measures, to some extent, how the notion of horizontal lift that's given by this connection, to what extent this is non-integrable. Okay, and so that was this curvature. curvature FA, and this is a two-form, and it was given by the exterior derivative of A. So the A is a one-form, the exterior derivative is a two-form, plus essentially the exterior product of A with itself, which is a two-form, and then bracketed because, right, so since A take values in G, if I just took the exterior product with itself, that would take values in G tensor G, and I want to go back to G itself. And so this bracket here is, right, so this, I can view it as a linear map from G tensor G back to G. And what it does is it sort of maps AB to the Lie bracket between A and B, right? So that was the curvature, and then once you have this notion of curvature, then you have the Young-Mills action, which is really basically just the L2 norm of the curvature squared. Okay, so that's the Young-Mills action. And we've seen that, so there's a natural, this gauge group, which we call sort of curly G, which are the functions G from the torus into the group. And we've seen that this guy, we think of elements of this group here as being something like changes of coordinates on this guy, which act on this space by just multiplying, right, at every point X in the torus. You have a rotation, if you want, on G, which is just given by left multiplication with the element G of X. Okay, so that's some kind of change of coordinates on this space. And so then we have a natural way, we've derived a natural way in which the fields A change under this change of coordinates. And then similarly for the curvature. And so we've seen that actually the curvature, right, so we've seen that the curvature F associated to AG, which would be sort of A acted upon by such a change of coordinate, we've seen that this is just the conjugation of FA with G. And so in particular, if I call this action, say, S of A, so in particular, we've seen that S of AG is equal to S of A. So we have this invariance of the action under this gauge group. And I mentioned that also the physical observables of the system should only be functions of the field that are themselves invariant under the action of the gauge group. And so now what I want to do, the first thing I wanted to do today is to just discuss a very large class of such actions, of such observables. Right? So one thing that you can do is you can take, okay, so there's one important function on the Lie algebra, which is invariant, or, well, either the Lie algebra or the Lie group. So if you think of G as being, you know, groups of, so we always think of G as being groups of matrices, okay? So think of G as being something like SON or something, or SUN or something like this, okay? And so you have a notion of trace. And one important fact of the trace is that it's what's called a class function, right? So that if you take the trace of a matrix, it's the same as if you take the trace of that matrix conjugated with another matrix, right? Because of the sort of circular property of the trace, and then you can put the G minus 1 on the other side and it cancels out, right? And so now if you have such a class function, so for example, one way of building something invariant is to just take the trace of that guy, right? So if I take the trace of that guy, then because of what I just said, the G's cancel out, and then you see that you obtain something which doesn't depend on the little g. Okay, so that's an example of an observable which is invariant under the action of the gauge group. And there's a larger class of such observables, which is very natural, which is called Wilson loop observables, or just holonomies, if you want. And they are obtained in the following way. So say Wilson loops. So you have your space TD. Okay, so let me draw it. So let's take D equal 2. It's sort of two-dimensional. So that's my base space TD. And now I take a loop in there. Okay, so just a smooth function, say from the circle into TD, but it's a based loop, right? So say, actually in the end it doesn't matter, but so say I have a starting point and then I go around the loop and I end up at the same point that I started from, okay? Now, remember we've seen that there's a natural way. So now we have this copy of G that's sort of attached at every point, okay? And we've seen that in P, the connection A gives you, it determines these horizontal subspaces at every point in P, right? And so now what you can do is you can try to lift this loop. Maybe I should use colors actually. Let's use red. So in red is what's happening in P, and in white is what's happening in TD. Okay, so here you have these copies of G that are attached at every point. And now you can take that guy and try to lift it to a curve in P, which is such that at every point here, right, so at every point here, it sort of belongs to, right, like the copy of G that sits above the corresponding point on the white curve, right? And furthermore, the red curve, so it starts at the identity here. So say, right, I have my copy of G here, just assume that I have a choice of identity somewhere. So I start at this point, and then the red curve is such that at every moment it projects down to the white curve, right? So the red curve lives in here, whereas the white curve lives in here. But there's a projection, which is just forget about that copy of G, right? In general, it's given by that map pi. And so I want the projection of the red curve to be given by the white curve. And furthermore, at every moment, the tangent vector of the red curve should belong to the horizontal subspace, right? And then there's obviously, because of that decomposition, direct sum decomposition, there's a unique way of doing that, right? So there's a unique way of doing that, so that gives me the red curve. But the important thing here is that even though the white curve closes up, there's no reason in general for the red curve to close up, right? So you know that by the time you've gone around the loop, the red guy is going to end up in the same fiber as where it started from, but it doesn't necessarily end up at the same point in that fiber, right? So there's no reason for it to end up in the same point. And right, so now so this gives you a function, right? So given the loop, you have a function, say, Hall, that takes loop times connection into an element of G, which is the element that tells you, you know, what's the element that maps the starting point here to the end point here, right? Okay. Now, it's a sort of an exercise to show that if you take Hall of, say, a given loop and the A, which is acted upon by this gauge group, then what you end up with is Hall LA and just conjugate it with a G of X inverse, where X or X0, say, where X0 is that, you know, the base point of your loop. Okay? So that's you know, that's basically a calculation that one can do. And so in particular, if you take the trace of that, then it doesn't depend on G, right? So if you take the trace of a holonomy around any loop, then that gives you an observable which is independent of G. Okay, so that's a natural, somehow, class of observables. And you see that they are sort of related to the curvature in the sense that if your connection is flat, if the curvature is 0, then that's the case where here you always actually end up at, like, the red loop would actually close up always, okay? And so the curvature, having non-zero curvature is basically the same as, you know, these guys being non-zero, or some of these guys being non-zero. Okay? And actually it's a sort of a theorem that if you take, okay, so in general here, instead of taking the trace, you can apply any class function of G, right? So if you have any function from G to R, which has the property that it's invariant under conjugation, well then, you know, because that also gives you an observable. And so in general, depending on the Lie group, you know, either just taking the trace is sort of enough, or you might have to look at other class functions. But in any case, so that gives you now a bunch of observables, and it turns out that actually every single observable can be recovered from the Wilson loop observable. So in some sense, that's all the observables there are. Like if you take any other observable, so if you take any other function of the connection which is invariant under the gauge group, you know, it's a theorem that you can actually approximate that by some function that only depends on these Wilson loop observables. Okay, so basically these are sort of exhaustive, if you want. So if you know all of these Wilson loop observables, then you know in which equivalence class your connection lives. Okay, equivalence class under the action of the curly G. Okay, so as a particular case, that would include determinants, yes. So, okay, so that's the Wilson loops. So now let me just, so these are, one thing which is somewhat important about these Wilson loops is they are sort of local observables, right? So the Wilson loop really only depends on what, I mean, it's kind of clear from the definition, right? I mean, it only depends on what A does on this loop, right? If I change A anywhere outside the loop, then obviously this guy is not going to change, right? It's clear. So it's somehow the analog of like local observables in this theory. So now one thing I just wanted to quickly discuss was that the fact that in the particular case where G is just U1, so just a unit circle, then you recover Maxwell's equations from the Young-Mills action. In particular, so the way you recover Maxwell's equation is as the Euler-Lagrange equations for that guy. So it's basically the stationary points of this action. And so how do you do that? So let me just do a small aside. So now that's the case where D is 4, and you look at Minkowski space. And so since it's dimension 4, what I'm going to do is I consider time to be the 0th coordinate. Okay, so that's sort of maybe a nicer way of writing things. So instead of my indices going from 1 to D, now they go from 0 to D, and D is still 3 somehow. Right? And now in this case, the A, right, so A is a 1 form. What does it correspond to in electrodynamics? Well, there's an A0, and then there are the AIs from 1 to 3, okay? So A0 corresponds to the electric potential. And the AIs corresponds to what's called the vector potential in electrodynamics. Okay, so that's a vector because I still goes from 1 to 3. Okay, that guy is just a scalar function. So that I would also call it V, because that's just the V in electrodynamics, whereas the AIs are the thing that people already call AI in electrodynamics. Okay, so it's the same AI as the AI in electrodynamics. And so then, now these are real valued, right? Because if G is U1, then the Lie algebra is just R. Okay, so each of these AIs and the A0, they are just real valued functions in the case of U1. And then what is F, right? So FA is now a two form, remember? So it's the exterior derivative, and then there is this bit here. But this bit here vanishes because, of course, on R, there's no Lie bracket. The Lie bracket is 0, right? U1 is abelian, so everything commutes. So this guy vanishes. So FA is really just the exterior derivative. And so you would write it as a matrix, right? So the FA is a two form, so it's a matrix really, right? You can view it as a matrix valued function, so you have the Fij's. And then if you write it as a matrix, what you have, so it's antisymmetric. So it's a 4x4 matrix, sort of antisymmetric. And then here you have three vectors. So in this column, what do you have? You have sort of the time derivative of this guy, right? The first coordinate or the 0th coordinate is the time direction, right? And so Fij is Diaj minus Djai. That's what the exterior derivative does. And so the first column here is the one where you have sort of D0 AI minus DIA0. And so it's so in this column, what you see, if I write it in usual vector notations, you have basically the time derivative of the vector potential minus the gradient of the electric potential, right? So that's the Diaj minus Djai, where if I write dt instead of d0 and gradient instead of di, as you would usually do in sort of normal vector calculus. And then you have three more entries here, right? And these three entries, I can also view it as a vector, right? So you have three entries, so that gives me a vector. And the way I view it as a vector is that the ijth entry, I view it as the kth component of a vector with a sign which depends on whether the ijk permutation is sort of even or odd, right? So that's the usual way of turning a 3x3 antisymmetric matrix, of identifying, right, a 3x3 antisymmetric matrix with a three-dimensional vector. And so if you do the calculation and you look at what that, so what's that vector? Sort of the ij component here, it's just Diaj minus Djai. And if you look at the vector, so that the kth component of that is what I just said, well, that's the curl, right? That's the definition of the curl. So what's here is the curl of A, okay? And so the action, now S of A, or AV if you want, is, so what is it? So it's the integral now of the curl of A square, and then minus, because of Minkowski, okay, minus this dTA minus gradient V square, right? So why do these guys come with a minus and that with a plus? Right? It's because in the Minkowski metric, remember we have to use the metric in order to contract. We basically look at the L2 norm of F, but we use the metric to contract the indices. And so the ij index gets contracted by using the ith well, the metric is diagonal, so you just look at the ith guy on the diagonal times the jth guy on the diagonal. So what does that mean? It means that the II guys come with a plus sign, right? So this comes with a plus sign when I contract. The 0, 0 guy comes with a plus sign. And the 0i guys come with a minus sign, right? Because of the Minkowski metric. So everything that's here comes with a minus sign, and everything that comes here comes with a minus sign, right? And so that's why what's here has a minus sign in front, whereas what's here has a plus sign in front, okay? So that's now my action in this particular case, and the integral here is over space and time, obviously. And so now I can look at the stationary equations, right? So I look at just the equations derivative of the action is equal to 0, right? So I just take the functional derivative of the action and I set it equal to 0. So that's, you want the equations, the Euler-Lagrange equations. And here, of course, it's very easy because this is quadratic, right? So it's quite easy to take the derivative. So all you have to do, right? So if you have a quadratic form with some operator in there, taking the functional derivative basically means looking at the sort of operator times its adjoint acting on the thing. So what do I get if I do that here? Well, on the one hand, I get, if I take first the functional derivative, well, okay, so maybe I should, okay, so I keep the A's and the V's separate. So I have this and this, okay? So now let's first take the functional derivative in the V direction because the V guy only shows up once. So in the V direction, well, what you get is, well, the adjoint of the gradient is divergence, right? And so what you find is just the divergence of this expression should be 0, right? So that tells me that the divergence of dTA minus gradient V should be 0, okay? And on the other hand, if I take the derivative in the A direction, right, so what do I get? So from this guy, well, if you do the calculation, you find that the adjoint of the curve, oh, here, yeah, I mean, of course, there's a minus which comes from the minus, but there's another minus which comes from the fact that the derivative of the adjoint of the gradient is minus the divergence, so, and in any case, it's equal to 0, so it doesn't matter. Now for A, the adjoint of the curl, you can do the calculation, you figure out that the adjoint of the curl is actually the curl, but with a plus sign, not with a minus sign. Okay, so the adjoint of curl is really curl, not minus curl. And so then from this bit, you find that you just get the curl of the curl. And then from this bit, well, the adjoint of dt is minus dt, okay? But then there's an extra minus here, so the two minuses cancel out, and so you get plus dt of this same thing, dta minus gradient v is equal to 0. And so now the claim is that if you do the link with electrodynamics, well, this guy is the electric field, right? Whereas this guy is the magnetic field, right? And so then what do these equations say? Well, this guy really just says that the divergence of the electric field is 0. So here, okay, so maybe I should have mentioned this. So everything I said here, everything I mentioned so far is about, if you want, pure Young-Mills. And so pure Young-Mills in some sense describes like the vacuum. So if there's no matter around that interacts with it. So in the case of electrodynamics, pure Young-Mills would describe Maxwell's equation, but in the absence of, currents or charges. So that's why here you get a 0 on the right-hand side. And then here, well, you get that the time derivative, so this here is the same as that, right? That's the E. And here, well, it's the curl of B. Right, so that's one of Maxwell's equation. And then, well, the other Maxwell equation, you find it by just saying, well, remember the definition of E is dTA minus gradient V. So one thing I can do is I can just take the curl of this expression, and I find, so where is that? Oh, sorry. Yes. Right. Yes. So I have this expression here, right, which is that E is equal to dTA minus gradient V. And I can also take the curl of this expression, right? So that was just the definition of E, if you want. I can take the curl of this expression, then the curl of a gradient is 0. And so what do I find? I find that dTB, which is the curl of A, is equal to the curl of E, and so it's minus curl of E is equal to 0, right? And this is that's exactly Maxwell's equation. Okay. So that was just to show you the link, right? So Maxwell electrodynamics is just Young-Mills in the case of U1, and then the connection here is just the electrodynamics potentials, right? Sort of the scalar, the electric potential, and the vector potential. And you see this whole gauge invariance, so this gauge group here, so that's just, arbitrary function from R4 to R. And the way things transform, if you do the calculation, well, you find it transforms it in exactly the way that keeps E and B the same. Right? So you can find that if you take any function of space-time, and then you add to B the gradient of that function, then it doesn't change B, right? Because if you add to A the gradient of that function, it doesn't change B because the curl of a gradient is 0. Okay? And if you add to V the time derivative of that function minus the divergence, it's just the, okay, maybe I should actually just do the calculation. I'm going to confuse myself. Right, so we've seen how A transforms, right? So the way that A transforms was by conjugation, but conjugation in an abelian group does nothing. And then there's this minus dGg inverse, right? Which really means that it just basically, you just add the gradient of G. So the way that A transforms is you just have an arbitrary function G, and you just add the gradient, but it's the space-time gradient. So you add to V the time derivative, and you add to A the actual spatial gradient, right? And then that's what I just said, is that B doesn't change because you add to A the spatial gradient and the curl of the gradient is 0. And then this guy hopefully doesn't change either, right? Because here you get the time derivative of the gradient minus the gradient of the time derivative. And so then that's 0 as well, right? And so neither B nor E changes under the action of the gauge group. And then, of course, that's what we're so familiar with. In electrodynamics, you can measure the fields, but you cannot measure the potentials. Right? The potentials are kind of ill-defined. Okay, so that was just the aside. But that also shows that, right, so what we are describing here is this pure Young-Mills, which really describes the vacuum. if you wanted to describe something more realistic, you should add matter to this whole thing, but you can do that. And actually, in the second of the two papers that I mentioned, we actually write down the sort of more general system, but it doesn't, from the point of view of the sort of the technicalities or the probability theory or regularity structures and so on, it doesn't make any difference. Okay, and so I'm going to keep the simpler case. But yeah, because here, right, so here you have made a choice of Minkowski space, but the underlying space here could be anything. Right, so here in this, it doesn't matter what this space is, you can choose the metric on that space. Okay. Okay, so now we go back to probability. So remember what we mentioned towards the end last time is that we really want to somehow define some kind of measure that would be in some sort of end goal to define some kind of probability measure on connections, or actually on, you really want just connections modulo gauge group. So you really want somehow a probability measure on the space of gauge orbits, which in some sense corresponds to this formal expression, right? Or this formal expression may be pushed onto the space of equivalence classes of these connections. So, and then what I sort of very quickly mentioned towards the end was that, you know, you might want to use the fact that if you take an arbitrary, if you take a measure of the form e to the minus v of x dx on Rn, then this measure is invariant for the SDE dx is equal to minus gradient v of x dt plus square root of 2 dw, right? So why is that the case? Well, all we have to check, right? So if I call this measure mu of x, all we have to check is that if I take any smooth function and I look at the integral of the generator of this diffusion applied to my smooth function, and then I integrate it against e to the minus v of x dx, I want to show that this is 0, right? But what's the generator? So the generator is just, so the reason there's a square root of 2 here is that it makes the generator of that guy the Laplacian and not a half the Laplacian, right? So then this is just the integral of the Laplacian, which I write as the, well, let me just write it as the gradient divergence. Yeah, maybe I want to write the Laplacian as the divergence of the gradient. Okay, so I have the Laplacian, which is divergence of the gradient, and then minus the gradient of v times the gradient of f. Right, so this is just this expression here. That's the generator of this guy. And now all I do is I do one integration by parts to get rid of that divergence, right? So what do I get? If I get, now of course oh no, the signs are fine, yeah. So if I get rid of, I do one integration by parts, right? So the divergence here becomes a minus gradient acting on that guy. And so minus gradient acting on this thing pulls down plus gradient v, right? Because there's another minus here. And so then this divergence basically turns into a gradient v, and you see that these two expressions are the same, and so obviously then this is 0, okay? So this measure is invariant for this process. And so the idea then is to say, well, okay, so I just do the same thing here, right? So I just write down the equation for which that guy is supposed to be invariant. Right? And I just don't care about the fact that everything's infinite dimensional. And so what happens when I do this? Okay, well, quite a bit of time. So formally, so this is invariant for the following SPD. So now my variable is A, right? So I have a dA is equal to minus, well, the derivative of S of A somehow in the direction A, dt plus, square root of 2 dw. Now, here one has to be a little bit careful, right? So when you take functional derivatives, or actually even when you take a gradient, right? So like what we did in the previous calculation, when you take a gradient, you have to actually say how you take the gradient, right? So the gradient is not an intrinsic notion, right? So what's intrinsic is the differential of a function, but the differential doesn't give you a vector, the differential gives you a form. And then to turn a form into a vector, you need a metric, right? So you have to say which metric you use in order to turn the differential into the gradient. In the calculation that I just did, I was just implicitly using the Euclidean metrics. So now on functions, well, I have to be a little bit careful about what metric I want to use. But of course, here there's a natural sort of L2 metric, right? So there's the natural L2 metric, which is basically the one that we used to define the action in the first place, right? So we have sort of L2 over the base space, and then these guys take values in this Lie algebra, but we have a natural norm in there. And so we do have a natural metric that comes with it. And so then the noise here should really be the Gaussian process that is white in time and has as its covariance that metric, right? The covariance structure should be compatible with the metric that you've chosen in order to define the gradient. And so now you've seen this morning, actually, in the exercise session, that white noise is precisely the Gaussian process that's sort of compatible with the L2 norm, right? So we've seen that white noise is basically just the sort of isonormal Gaussian process for the Hilbert space L2, okay? And so here you have to take white noise, well, space-time white noise, right, which is the same, well, space-time white noise, which is isonormal for L2, L2 in space and time. It's the same definition as this morning, except that then it's a sort of a Gothic G-valued space-time white noise, right? But then it just means that it's also isonormal with respect to the scalar product that you've got on G. Okay, so it's isonormal not in just the L2, but L2 with values in G. And actually L2 with, it's on the forms, so you have to also take, but each one of the three components of A would just be independent. Right? So you just have, so this is the noise which is kind of as white as possible if you want. And so here, this gradient is some kind of L2 gradient of this action functional. So now if you do the calculation, I think Harpreet is going to do that in one of the exercise sessions. What you find is that this here is really just minus the L2 adjoint of this covariant derivative acting on the curvature guy. So that's another way. Right, so you get this, this expression here. And maybe one thing which is maybe somewhat important already is that if we you know, if we expand this a bit further, right? So we have an expression for FA, which is this. And then the DA, that was, so I didn't write it here. So let me just remind you. So DA is basically just a normal exterior derivative plus somehow the exterior product with A and some sort of Lie bracket in there. Right, that was the definition of the covariant derivative. So if we take the adjoint of that, well, it's going to be the adjoint of D, which is D star. We've seen that okay, so here we're going to get basically something like a D star DA, right? And then we're going to get other stuff, which for the moment I'm going to ignore. I'm going to show you in a second what it is. And then we have the space-time white noise. Right? So here, maybe let me put a DT. Okay, so we get something of that type. And when I put ... here, so this is going to be nonlinear stuff, but it's going to involve only first-order derivatives of A, right? So the only term that has a second derivative of A is that term here, right? Because the adjoint of this, clearly, you know, it's the D guy plus some sort of zero-order differential operator. And so then when it acts on this, the only way I get a second-order term is by having the D star acting on the D here. Okay, everything else is either first order or zero order. Okay, so that's the only second derivative that shows up. So now we've seen, well, okay, we haven't really seen it yet, but so this whole regularity structure business works very well for right? So it was important in what we saw in Lorenzo's course this morning and also in the exercise sessions. It was important that this integration operator was a, you know, convolution with a kernel. These kernels, they were supposed to be like Green's function of the linear part of the equation that you're trying to solve, like in the exercise class where it was the Green's function of the Laplacian. So here you have a sort of a parabolic equation, so it would be the Green's function of dt plus d star d. And it was important that this Green's function is basically smooth everywhere except at the origin where it has a singularity of certain order. Okay. Now, if this was the Laplacian, right? If A was a scalar function, then D would just be the gradient. D star would be the divergence. And so you would just have divergence of gradient, which is the Laplacian, okay? And then your Green's function would just be the heat kernel. And the heat kernel is precisely of the type of the kind of kernel that Lorenzo was happy with this morning, right? So the heat kernel is smooth everywhere except at 0. And 0 meaning really t equals 0 and x equals 0. That's the only point where you have a singularity in the heat kernel. And the singularity is sort of well controlled, okay, and it's smooth outside. Now, A is not a scalar function, but it's a one form. And so then on one forms, if you do the calculation here, what you find is that, well, sort of know already, right? So we've just seen in the derivation of Maxwell's equation that on one forms, the D guy here is basically more like a curl. And now, if you have a curl here, it means that I can add to A the gradient of anything. You get 0, right? So that's the fact that, you know, in differential geometry, you know that B composed with D is always 0. And so this guy is a one form. I can always add to it the D of a 0 form, which is just the gradient of a function, right? And I would get 0. So that means that this guy here has an infinite dimensional kernel, which corresponds of all the exact differentials, right? So of all the gradients of scalar functions. So all of these guys are in the kernel of this guy. So there's a huge kernel here. So it's not elliptic at all. right? It sort of looks like a Laplacian, but it's really not. So it has a very huge kernel. And so which means that this equation here, it sort of looks parabolic, but it's not. And the Green's function doesn't have the nice property that Lorenzo wanted this morning, right? So then that's a problem. And that would be a huge problem, right? Because it means that this guy, normally the heat equation has really nice regularization properties, right? We've seen this morning, you basically gain 2 degrees of regularity when you hit anything with a heat kernel. And so if we had here like a heat equation, then even though this guy is very irregular, so we've seen this morning that white noise has regularity basically minus dimension over 2, but here the dimension is really the space-time dimension, so it's quite irregular. So if we had the heat kernel, then at least the A would be 2 degrees more regular than the space-time white noise, which is still bad, but it's 2 degrees less bad. Whereas if you have a huge kernel of that guy, then in sort of all the directions of that kernel, this guy has no smoothing properties at all. And so it means that even if you can somehow and to have any chance of giving a meaning to this equation, well, the A guy would basically look like white noise. It would sort of, you wouldn't expect the A guy to look any better than white noise. Then that means that all of the nonlinear things here are going to be horrible. Right? So like sticking white noise into nonlinear operations is usually a really bad idea. Okay. And so you can sort of formally derive some sort of equation, and then you're stuck. And then you're like, okay, there's no chance of this making any sense, even using regularity structures or whatever, right? So now we have to use the fact that, well, we don't really care about this measure here. We only care about sort of the push forward of this measure under the operation of, taking equivalence classes, right? So we only care about the equivalence classes of A, under the action of that gauge group. We only care about those gauge orbits of A, okay? So how does that help us? Well, yeah, so let's erase that. So first, this equation here, let's be bold again and sort of pretend that it does have a chance of making sense, even if it doesn't, okay? So let's see how this equation here transforms under changes of coordinates, right, under the action of the gauge group. So I thought I'd written that somewhere. Okay, no. Anyway, so how does this transform under the action of the gauge group? So if I take a fixed element of this curly G, right? So I just take a fixed element AG, right? So if I fix G and say I assume that A, which now depends on time, also solves this equation, right? So let's give it a name, star, solve star, even if, we've just discussed that there's no chance in hell of giving a meaning to that equation, but let's forget about that discussion and think again that we might be able to solve it. So assume that you have a solution to that. And now, let's just brutally try to write down, the equation for AG, right? So remember, AG is GAG inverse minus DG G inverse. And this derivative here is space derivative, right? So G here is a fixed element, so it doesn't depend on time, right? So now this time here, the dt this time here is an extra time which has nothing to do with, you know, this space, and, you know, has nothing to do with, right, in Maxwell's equation, the time that shows up there was really one of the directions of this space here. Now here I consider all the directions of that space as being space, okay? And the time here is just a completely fictitious time which has nothing to do with physics, if you want, right? So it's a completely mathematical device. And so here the G is fixed, and so it doesn't depend on time. So if I take the time differential, then this guy drops out, right? So this guy doesn't have any time in it. And so what do I get? Well, I get basically just conjugating everything here with G, right? Because I just get that. But now this guy here, right? So I get minus, if you want, G, dA star FA, G inverse, plus square root of 2, G dW of G inverse. Now this guy here, we've seen that that guy is an actual two form. So that guy really transforms simply by conjugation. Right? Exterior derivative, we've also seen that it's sort of covariant in the right way, in the sense that it's simply the exterior derivative for AG is simply, it sort of, it behaves in the correct way. So what does that tell us? So it tells us that this guy, and that's something one can also just do it as a calculation, right? So it's an explicit calculation you can do. What you find out here is that this is just minus dAg star of FAG dt plus square root of 2g dWg inverse, right? So this bit is exactly the same equation as we started from, right? And that's not surprising, right? Because we had this action functional we've seen is invariant under the action of G, and then we've taken the gradient flow for that guy. And so, of course, the gradient flow for that guy should itself also be invariant under the action of G, right? If the action functional itself is. So that gradient flow, it's not surprising that it's invariant under the action of G. And then we have this term here. But now, remember, we've chosen our norm, right? The norm in the Lie algebra here was chosen in such a way that it's invariant under conjugation by elements of G, right? So this here, this conjugation, so this is a pointwise thing, right? So at every x, you have sort of pointwise conjugation, which is actually an orthogonal transformation, because by definition, right, we assumed that the norm that we've chosen on the Lie algebra G is the norm which is invariant under these operations, which makes all these operations orthogonal, right? But now if you have a white noise and you act with something orthogonal on it, you know that by, you know, Ito's formula, you know that it doesn't change the law, right? So this guy in law is equal to dW itself, right? So not pathwise, but in law, just by Ito isometry. Okay, so this is really Ito isometry. So here, Ito isometry. Okay. So that's the leftover from the gauge invariant, right? So the equation here, formally, it's gauge invariant, but it's sort of gauge invariant in law. Okay, you have to be a little bit careful of how you compare things when you act on them with the gauge group. Yeah. But okay, so we have a guy like that, which is sort of nice and gauge invariant. And all we care, right? So now the cartoon you should have in mind is the following, right? So that's, if you want, what's in yellow here the equivalence classes, right? So the board here is the space of A's. So you have an A here. And say here you have an AG, where you act on A with an element of your gauge group. And these guys are all equivalent, right? And so what we really care about is not the process on the space of A's, but it's really just the process on the space of yellow curves, right? So this point and this point are just identified, okay? So now, what does that mean? It means that, so we have this, at least formally, we have this process here, which, because it's not going to exist, but let's pretend it does. Right? So we have formally, we have some guy, like some kind of stochastic process here. And now, well, this guy is very badly behaved. We don't think it exists. So we want to somehow change it in a way that makes it have a better chance of existing. Okay. But on the other hand, at least formally, it shouldn't change what you get when you project onto the space of gauge orbits, right? And so how do you do that? Well, this guy sort of solves some kind of stochastic differential equation. What we could do is at every point, we could sort of push it, in the direction of the yellow curves, right? So if I push the guy a bit further, so say if I make it even more brutally, right? So at this point, I decide to just jump here and then continue, right? Then because of what the calculation we just did, what you end up with at the final time in law, well, it's not going to be the same, but it's going to be the same modulo, right? So if I identify connections that only differ by the action of the gauge group, then in law, I don't see that jump, right? Because, well, this point and this point, they're identified anyway, okay? And we've just seen that if you start from here or if you start from here, the two solutions in law, they are the same and they really only differ by, conjugation by G. So this jump that you've done here halfway through is actually completely invisible by the time you project down onto gauge orbits, right? So instead of making discrete jumps like that, we could just as well make sort of, lots of little jumps all the time, which really means we simply add an extra drift to the right-hand side, provided that the drift points in directions that are tangent to the gauge group, okay? So the idea now is to say, well, instead of looking at this equation here, which we have basically no chance of being able to make sense of, we look at an equation of that type where we add here an extra term, which is going to be a term that always points in the direction of the gauge orbits, right? At every point in that space of connections, it's a drift term that sort of points in the direction of these gauge orbits, right? Which are themselves sort of infinite dimensional subspaces. Okay, so now that's a trick so that trick was introduced actually a long time ago, so in the 80s by the Turk, who was at the time, so he was actually studying the Ricci flow. And in the Ricci flow, you have a similar sort of problem, right? Because you look at the flow on spaces of metrics, and again, like, or spaces of Riemannian manifolds, if you want. And of course, manifolds are only defined, right? So if you have two manifolds and they differ by a change of coordinates, then you consider them to be the same, right? So you also have a big symmetry that acts on the space of Riemannian manifolds, which is just all the changes of coordinates, right? And so you sort of push the metric forward under the change of coordinate in the right way. And so what he realizes, if you sort of write down the Ricci flow naively, well, you get a sort of badly behaved equation. It's sort of a similar thing. You end up with an equation which sort of looks parabolic, but is not. But then you can actually add a term like that to make it parabolic. And then a bit later, so Donaldson then actually realized that the same trick works in the case of Young-Mills. Okay, so that's Donaldson, the Turk. Okay, I never know if I think there's a C in the Turk. So what term should we add here, right? So what are the terms that actually point in the yellow directions? Right? Well, that's all the terms, right? So it's basically look at AG for an infinitesimal G. Right? That's basically what you want to do. Right? Because you have A, and then AG is sort of a guy which is further away. If you want to be very close here, essentially you want to take a G which is very close to the identity here, right? Which basically means you want to sort of differentiate this expression in the G direction at G equals 0. Right? That's what you want to do. So you want to just replace that G here by something which is extremely close to the identity, which means that it's basically 1 plus epsilon times an element of the Lie algebra, right? So formally, right? And then you want to kind of differentiate in epsilon, just keep the first order in epsilon, and then that sort of gives you the tangent directions here. Okay. So what you get if you do that, right? So I just take, okay, I can erase that bit. Right, so I look at A of, you want 1 plus epsilon G, and now this G, I think of it as being, right, that guy is valued in the Lie algebra, but of course I'm sort of cheating because I'm not really allowed to do that. But if you think of all of these things as being matrices, then you're kind of fine, right? So then what is this? So this is, 1 plus epsilon G, A, up to first order, while the inverse of 1 plus epsilon G is just 1 minus epsilon G. Right? So here I just have 1 minus epsilon G. And then I have minus the derivative of 1 is, of course, 0. And so I get an epsilon dg times 1 plus epsilon G inverse, which is, again, minus epsilon G. And then there is a, right, and that's it, actually. And so, of course, now I want to keep the first order in epsilon. So here there's already an epsilon out there, so I just drop that guy. And here, well, you see you get an epsilon times GA minus AG, so you get the bracket between G and A, and minus dg, right? So you just get that. And this I can actually write it as minus dAg, right? So this is actually just the covariant derivative applied to the G, and the G was arbitrary, right? You look perplexed. Yeah? Okay. Okay, so we've seen now sort of these directions are basically all the guys that are of the form dA of G, where this G here is just an arbitrary, right? So that's like an infinitesimal version of that guy. So that's an arbitrary, say, smooth or regular enough function from the torus into the Lie algebra. Right, so this is just a G-valued function on the torus. So we can add to the right-hand side here anything of the form dA of something. Okay, so anything of the form dA of something, formally, pushes us in that direction, right? So it's like a sort of infinitesimal gauge transformation that we sort of do at every moment of time. And so now what should we add? Well, you know, here we have a d star d that shows up. And well, I just argued that d star d is not elliptic. But then if you've ever sat in any sort of differential geometry course, you've seen that there is actually a nice elliptic guy, which is d star d plus dd star. Then that guy is just the Laplacian. Yeah, did you have a question? Mm-hmm. Yeah. Okay. Yeah. Yeah. Right. So, okay. So here, right. So I just so here the d star d guy is not elliptic, but if we had a d star d plus dd star, then that would be elliptic. Right? And now we're sort of in good shape because we're allowed to add anything of the form d of something. Right? And so then why don't we just add d of d star a? So then the natural term to add here is to add minus dA star of dA of ds dA of d star a, right? So now at least formally, right, if we believe that all of this was justified, of course I justified absolutely nothing, if we believe that this whole thing can be justified, then as far as equivalence classes of A are concerned, the dynamic of this equation here should be the same as the one that we derived in the first place, right? Because of the argument that I just gave you over there. But this one now has a much better chance of, you know, being somehow well posed in some sort of way, right? So, okay, so now I don't want to go into sort of too much details of what the equation looks like. So now from now on, in some sense, the exact form of the equation at this point for a moment doesn't really matter to us. So let me just write down the general form of the thing that we get. So we end up with something that's like dA is equal to Laplacian A, which comes from the d star d plus dd star, at least the d bit of that, right? And then we have all kind of nonlinear things. But the nonlinear stuff that we end up with, so what's the form? So there's going to be first order stuff. And the first order stuff is always going to be basically some bilinear form of dA and of A, right? Because how do you get a first order thing? If I apply dA star to this whole thing, then either I have a derivative that hits this guy here, or I have the A that hits this guy here. Right? In both cases, I get something which is quadratic in A and has basically one factor that is an A with a derivative in front and one factor that's an A without a derivative. Okay? So I never get things like derivative of A squared. Okay? Or just derivative of A by itself without anything else. Right? So I always get something which is like a derivative of A paired up with an A. So the first order bit is going to be some bilinear form of the derivative of A and A. Right? And then there's going to be cubic things because I have the A bit that hits, there's this guy which is quadratic in A, but then it gets hit with the dA star, which is a term which is linear in A. And so I have the linear in A guy that hits the quadratic in A guy, or multiplies the quadratic in A guy, so I get a cubic in A guy. And so I get like trilinear terms in A. Right, so it's like A. And that's basically all I ever get, right? Because here it's also of the same type, because the dA, there's the D guy, that creates the Laplacian, and then there's an A which combines with the D star A, and so it's again bilinear in A and the derivative of A, right? So all the terms that I get are either of this form, bilinear in A and derivative of A, or trilinear in A. And then these are just, there are different components. I have like DI, AJ, AK, and there are different ways of combining them. And you could, and you have Lie brackets hanging around and stuff like that. Okay. But so the important thing here is that it's of this form, well, dt. And then there's still the white noise, right? So the square root of 2 dw. So now let me first try to argue that at least if the dimension is strictly less than 4, then this equation is really not so badly behaved. Okay. And so why is that the case? So let's try to guess what's the regularity of this equation. Of this, yeah. Oh, yeah, there's dt's everywhere. Sure, yeah. So, so the space-time white noise, right? So now we have to do everything. We have to count regularity in a parabolic way, right? Because the heat equation is not invariant under the Euclidean scaling, it's invariant under the parabolic scaling, because there's one time derivative that balances up with two space derivatives. And that somehow says that in terms of counting regularities and stuff like that, it's as if the time direction counted like for two space directions, okay? So in some sense, effectively, the dimension of space-time, you have to think of it as being space dimension plus 2 and not space dimension plus 1, right? Because time sort of counts double under the parabolic scaling. And so it means that the regularity of white noise would be minus dimension plus 2 over 2, right? Space dimension plus the extra 2 that comes from time divided by 2, right? So it means that if, if the nonlinear bits didn't matter, right, then the regularity of A would be 2 better than that, okay? So it means A, you would have to, okay, so it's not quite in that space, right? So remember in Kolmogorov, you always lose a little bit. So there's a little minus here. So it's really in this space minus kappa for every kappa, and I just ignore that. I pretend it belongs to that space, which is a small lie. So the regularity of A is 2 better, right? So because the heat convolution with heat kernel gains you 2 degrees of regularity. So the same way as for the convolution with Green's function of the Laplacian. So you get 2 better, which is minus d minus 2 over 2. Right, so here already you see that you start to have trouble in dimension 2. Right, in dimension 2, this becomes negative. Of course, there's always this minus kappa, right? So in dimension 2, you have 0, but it's really just below 0. Okay. And so then already you see that, well, making sense of these terms is going to be problematic, because you have to take, cubes of distributions or squares, products of distributions and stuff like that. But okay, so that's somehow the regularity that you expect for A, the best possible regularity for A. And now if you somehow manage to make sense of this guy, so what kind of regularity could you at best hope? Well, the regularity of the dA guy would be at best, well, 1 less than the regularity of A. So that would be minus d minus 2 over 2 and an extra minus 1. And then it gets multiplied by A. And, well, if you multiply two guys of negative regularity, well, okay, normally you're not allowed to do it. But if it works out somehow, then the regularity of the product would be the sum of the regularities, right? So normally, if you multiply things of positive regularity, it would be the minimum of the two. But actually, you know, if it's of negative regularity, think of multiplying 1 over x by 1 over x, right? You get 1 over x squared. So if you have this sort of negative regularity, you think of it as being some sort of blow up of a certain speed. You multiply two guys like that, it's going to blow up like the product of the two. And so like the sum of the two speeds, right? So at best here, so here both are negative. We always take now dimension 2 or 3, say at least 2, and we're going to see that 4 becomes special. And that's why we're going to restrict ourselves to 2 or 3. So here at best you have this with then an extra minus d minus 2 over 2. And for the same reason, the trilinear term at best, you can hope to be in minus, well, 3 times d minus 2 over 2. Okay, so that's the best you can hope for. And now, if you want to have any sort of chance of being able to close some kind of fixed point argument for this equation, it better be the case that the regularity of these two guys is better than the regularity of that guy, right? Because if the regularity of one of these two guys is worse than that one, then the whole argument here was wrong in the first place, because then this guy would be actually worse, but then this guy would be even worse, and, you know, that sort of everything just falls down, right? You sort of go down to minus infinity, and so if you see that, okay, there's no chance of having any fixed point in any kind of space, right? So if you want any chance of this making sense, it better be that these two exponents here are better than this minus d plus 2 over 2, right? And so what you would want is, well, so if I multiply everything by 2, so I want minus 2 times d minus 2 minus 2 to be bigger than minus d plus 2, right? So that's in order to make sure that this exponent here is bigger than this exponent here. And so what does that tell us? So here I have a minus 2d. I put it on the right-hand side, so I get a d. And here I have a minus 2. So on the left, I have what? I have a 4 minus 2, which is a 2. And then I put that 2 on the left-hand side, I get a 4. Right? So d should be less than 4. I can do the same thing for the other guy, right? So I want that minus 3 times d minus 2 should be bigger than minus d plus 2. And then same thing, right? So I have a 2d now here, because I add the 3d to the minus d. And on the left, I have a 6. And I put the minus 2 on the left, and I get an 8. And again, d should be less than 4, right? So you see that as far as both of these terms are concerned, as soon as the dimension hits 4, you're in trouble. Okay, and of course 4 is just critical, and of course, no, 4 is the interesting one. But okay, so we can't do 4, but at least we can do 2 and 3. Right? So 2 and 3 here are the interesting dimensions in the sense that, well, there's a chance of being able to do something, but still all of these products are non-trivial, right? Because you have to multiply distributions and stuff. Yeah. Okay, so that's another question. Yeah, so you might have finite time explosion of this thing. Yeah. So of course that's not at all addressed by this kind of analysis. Yeah. Okay, so now so what did I want to do? Okay, so let me just first, for the last, how much time do I have? 8 minutes. Okay, sounds good. So So because of the, so thanks to this condition, right, that's exactly what you need in order to be able to apply this whole regularity structure business, right? So it turns out that, you know, if you use the whole machinery that Lorenzo has started to explain in his lectures, you can set up a fixed point problem for these guys, right? And, you know, you get unique local solutions to the fixed point problem, and so you have some kind of notion of solution. But there's a problem here, which is that, you know, in the same way as so in the case of rough path, remember, so if you're given, so first, this whole theory, what we've seen also this morning, is that things sort of split into two, right? So you also, for rough paths, you give yourself a rough path, and then if the rough path is given, then you can solve rough differential equations with it, right? And so, for example, if what you're given is just Brownian motion, then first thing you have to do is turn Brownian motion in a rough path, and that's non-unique, right? So you could either take the Ito lift or you could take the Stratonovich lift, and then depending on which one you use to drive your equation, you get either the Ito solution or the Stratonovich solution, right? In the case of regularity structures, you have exactly the same thing. So what Lorenzo started to explore, actually what we saw in the exercises this morning, was that, you know, you sort of start building, you break out your solution theory into some explicit stuff that you built from the noise, which is like the analog of the rough path, okay, which we call a model. And so that's just a bunch of multilinear expressions. So this morning it was something like k convolved with psi times psi, right? And then you have a theorem that says, oh, if somehow the k convolved with psi times psi makes sense, then the equation we saw this morning has a solution, maybe for small enough values of the constant b or whatever the name of the constant was. Okay, so you have to somehow give meaning to these multilinear expressions, just as in the case of rough path, you have to give meaning to the area process, and that you need stochastic analysis, right? So that the analysis alone doesn't tell you how to do that, okay? And so here you have exactly the same problems, which is that a priori, okay, so you have a big machinery that you use in order to solve that, but the first step in that big machinery is that this guy here needs to be somehow lifted to a model in, you know, for the regularity structure that's associated to this particular class of equations, right? And that's non-unique, right? So that lift is in principle non-unique, just in the same sense as Ito versus Stratonovich kind of thing, right? And so now you think, oh, so that's going to be trouble, right? Because it means that now, you know, I want to build that process, but that process, it should be one specific guy, right? It's no good saying, oh, you know, there's a family of possible processes that are sort of indexed by all the ways of lifting my noise, and every way of lifting my noise gives me a different process, and well, they're all in some sense solutions to this equation, right? Okay, and then which one's the right guy, right? So in the way I derived this whole thing, this is all incredibly rigid, right? So this formal calculation here, if you add here, right, so we did this sort of formal calculation which argued that this was gauge invariant. But if you add to the right-hand side any other sort of term of that type, it immediately breaks that calculation, right? So, it tells you that this is sort of very rigid. So you'd expect that there's really just one process that sort of like should be a good candidate. Whereas now potentially the theory would tell me, oh, there's a whole collection of guys, and you know, which one's better than any of the others. So what's the kind of statement? So let me first tell you what's the actual statement of the theory, and then you'll see what the problem is. And then, you know, in the next two lectures, we'll see, well, I guess in the last lecture, we'll see how that problem can be resolved. Right, so at the end of the day, okay, so on the one hand, you can say, oh, I solved this equation in, you know, using some big regularity structure machinery by assuming that I have some kind of lift of that noise, and then I solve it as solution of the fixed point argument, blah, blah, blah. But then at the end of the day, you want to still connect this to actual PDEs, and you can do that. And the kind of theorems that you end up proving are the following, right? So the following theorem, well, maybe I should put sort of theorem in quotation mark because I'm not going to make the statements sufficiently precise so that it actually qualifies as a theorem. But basically, so what do you do? So you look at some regularization of this equation, right? So you look at A epsilon plus this whole nonlinear bit. So dot, dot, dot means this guy plus that guy, right? That's dot, dot, dot. And in here, well, actually, let me actually write it really as a PDE. So dt for fixed epsilon, this is really going to be a PDE. And so here, and I forget about the square root of 2, it's sort of incorporated into the whole thing. And so I write here psi epsilon, like this morning. And so the psi epsilon is basically space-time white noise, which you've convolved with some nice smooth modifier, right? So psi epsilon here, you should think of it as space-time white noise convolved with some rho epsilon, where rho epsilon of Tx would be something like 1 over epsilon to the d plus 2 times rho of T over epsilon square x over epsilon. So you take a modification which sort of respects the parabolic scaling here. So this is so that it scales like a delta function. And rho is just some, nice compactly supported bump function that integrates to 1. Or maybe you want it to integrate to square root of 2, so you include the square root of 2 into the rho. But anyway, okay, so you just hit your space-time white noise with some smooth modifier. So now that's a smooth function. So this is just a normal PDE. Okay, it's a parabolic PDE, it has solutions. Okay, so there's no question that this guy has solutions. Maybe they blow up in finite time. Okay, but at least locally it has solutions. And so now the theorem is that, well, you look at that guy, and then there exists some constants, C epsilon, which depend in general on the choice of rho, such that if you actually, instead of looking at this equation here, so this equation here, in general, actually, it's just not going to converge. What you have to do is you have to add here a term of the form C epsilon times A epsilon. If you do that, for the correct constant, actually the constant ends up being negative in this way of writing it. So maybe I can put a minus sign in it, so then it's positive. So that these guys converge to a limit, right? So A epsilon converges to some limit A as epsilon goes to 0. And, in probability and locally in time somehow, right? So there might be blow up again, but the blow up, if there's a blow up, it happens after a time which, the blow up time doesn't go to 0 as epsilon goes to 0, right? So it remains out there. Okay, so there's a convergence to some limiting guy. And furthermore, you can choose the C epsilon in such a way that the A guy is independent of rho. Okay, it's independent of the choice of modifier. Okay, so on the one hand, that constant here depends on the choice of modifier, but the limit you get does not. Okay, so that's the kind of statement you get, and that you get in some sense for free once you have this whole regularity structure machinery. Then there's sort of general theorems about whole classes of equations, and this equation falls into one of these classes, and you just have a general theorem you can apply, and it tells you that. Okay, and so I'm just going to take this as a given. Right? This is a black box. You apply it, it tells you this. Okay, now what can you deduce from that? Or from that sort of things. This is now the problem is, you would want, what would you want? So on the one hand, oh yeah, so where does this converge, right? So this converges basically in these spaces with a minus kappa. Right? Okay, so the convergence here takes place in these kind of spaces. That's what the black box tells you. So first, these spaces are not nice because, for example, a guy like that, a distribution of that type in general, so if I just have an arbitrary element of that space and I know nothing more, then I have no way of restricting it to a curve. Right? So Wilson loop observables are dead. Right? So that's the favorite observables of anybody who does Young-Mills. If you just take a guy in that space, it belongs to that space in the sense that every component, every AI is an element of that space with values in that Lie algebra. I take a guy like this, well, I cannot define holonomies. And so it's a little bit of a shitty one form somehow. Right? That's why it doesn't really have a good interpretation of a one form. So that's one problem. Another problem is that on the face of it, I'm solving the wrong equation. Right? Because the equation that I wanted to solve is that one, and not the one where I add a guy here with a big constant, and furthermore, that constant is actually going to go to infinity, as epsilon goes to 0, right? So now if I look at this equation here, I told you that this gauge invariance calculation was extremely rigid. If I formally take the same equation and I just add a term constant times A, it's not going to be gauge invariant anymore, right? So that breaks the gauge invariance. And so, a priori, there's no reason to believe that this limiting guy is gauge invariant. Furthermore, here I said it looks like there's some kind of uniqueness, right? Because I said, there's a limiting guy and it's independent of rho. But then, of course, it's still completely arbitrary because, of course, if this guy has a limit, then clearly, this guy is going to have a limit as well. Right? I mean, that's not very difficult to prove. You just add a linear term, it doesn't actually, it's not very badly behaved. So this guy is also going to have a limit. And who tells me that this guy is any worse than that guy, right? Or I could replace the 5 by a -7. Why would the guy with a 0 here be better than anyone else? And actually, in a way, the proof, if you look at the proof, the way in which these constants are chosen actually depends on a whole bunch of arbitrary choices at some point, right? So you make like an arbitrary choice of compactifying the heat kernel or stuff like that. And if you make a different choice, you get different constants, and they're just going to differ from that one by some fixed number, right? And so what the black box here tells you is really you don't have one natural process, you have a sort of one parameter family of natural processes, and it doesn't tell you which one's better than the others, right? Or if there is one that's better than the others, right? So what you would want to know now is that there is actually a guy in that family which satisfies that sort of gauge invariance property, right, that we mentioned. So we had this formal calculation which tells us that the solution to this equation should be gauge invariant. Now we somehow use heavy machinery to produce a guy which we sort of claim is some sort of candidate for a solution to that equation. But, on the way, we sort of go through these approximations where clearly gauge invariance is broken. And, is there a chance of actually having it in the limit? Right? So that's not clear at all, probably. Okay. So, and then, and so that's basically the two questions that I want to address in the next two lectures, right? So the first question is the one about finding a good state space, because this state space is not nice, right? Because you can't define holonomies. It's not clear, right? It's not in that space, it's not even clear what that equivalence relation between the A's is, right? So I can, conjugating A with G is fine, provided that this function here is sufficiently regular, like if it's smooth, for example. But then if I quotient out by the smooth guys, we've seen yesterday that, quotienting out spaces of certain regularity by spaces of smooth functions gives you something that has a horrible topology. And so you would want to have a better way of, defining equivalence classes here. Okay, so tomorrow, is it after tomorrow, whatever. So in the next lecture, I'm going to sort of discuss the state space thing. And then in the last lecture, I'm going to discuss the gauge invariance thing. Okay, so that's in some sense the two problems that we want to address. Oh, okay, so that's it for today.
Thank you very much for this wonderful lecture. Any questions?
So you derive the equation from the action, that makes sense. But would other equations also make sense in the setting, such as the linear one, or it's very rigid, or say like a bilinear form of A and A? Can you also use the same machinery, or like to get gauge invariant ones? Or no, this is really the one equation that can be studied via those methods?
But so you have a choice. I mean, right, so if you're given a measure, there's clearly not uniqueness of the Markov process that has that measure as its invariant measure. Right? So already, even if I look at these gradient STEs, that's sort of the thing I mentioned in passing at some point, is that it depends on the choice of metric. And you could, I sort of, in the little calculation I did, I was choosing sort of the Euclidean metric, and I could have chosen a different one, and that would have given me a different STE. Right? So yeah, I mean, like here, there's actually choice, right? So I could have, instead of, in some sense, this is the whole, what I've written down here is what I get if I take sort of the L2 metric. So I take the L2 gradient, and then I take L2 for the covariance of that guy. I could do different things. Instead of taking L2, I could take H1 or H-1 or something like that. And I would get things that look a bit different. But in terms of all these calculations, it wouldn't actually change anything. I mean, like everything would be shifted by a certain amount or something like that. But at the end of the day, it wouldn't really change much. And taking L2 is kind of nice because then everything is local. I mean, otherwise you would end up with sort of weird convolution operators around. So,
yeah. Any other?
Could it be that your D = 4 problem became possible to be handled if you had convenient logarithmic corrections somewhere?
Yeah, so you would, that's what you would expect, right? So I mean, that's what people do. I mean, I don't know, when people say that Yang-Mills is renormalizable, and so you do some kind of, you look at the logarithmic corrections in some kind of RG analysis of this thing, and you see that it actually seems to behave reasonably nicely. So there is, I mean, I guess there is some sort of hope in principle that something could make sense in dimension 4. But this whole regularity structure business really relies on having a strict improvement of regularity somewhere, right? And so there, having these guys scaling in the same way as the noise just breaks the whole thing, right? So like that theory simply doesn't apply, but it doesn't mean that nothing else applies. Yeah.
Any other question?
This derivation seems very general to me. You know, it works for any gauge group. I would like to know if there is some, if someone did this, really wrote the equations for some specific group. Like, can I find these calculations, I mean, broken down for SU2 or for U1, and really the equations written?
Yeah, so, okay, so first in the abelian case, so for things like U1, from
Or
that
maybe
point of
SU2,
view,
I don't
all
know.
of these just drop, right? So then the nonlinear terms all just drop, and you just end up with the stochastic heat equation. And so from this point of view here, there's nothing interesting happening in the abelian case, right? So this is really just interesting. But yeah, for SU2, it doesn't seem, sure, I mean, you can, of course, one can somehow write things down, but I'm not sure it actually brings you that much. Sorry? Sure, but it might also just, give you a bunch of very heavy expressions where you kind of lose overview over what's going on because there's too much notation that shows up.
Any further question or comment? So please, after we thank Professor Martin Heyer, don't disperse. I have two important announcements. So the two announcements. First, tomorrow, just at the beginning of the coffee break, we have a group photo. So please don't disappear at that time. It's very important to have this photo. The second announcement that Professor Adriana mentioned yesterday, as in several other previous EBPs, we shall have a special volume of this school. And this volume will be published by Matemática Contemporânea, which is a journal of the Brazilian Mathematical Society. So you are all invited to submit a contribution. And the deadline for this will be November 30th. Okay, so the instructions will be afterwards given at the website of the school, but please keep that in mind. Thank you.
Hello?
So let's so I'll come again. Let's my pleasure to introduce Professor Constantino Salles from CBPF. Thank you very much, Professor. So let's start our talk, please.
Good afternoon. Well, I would like to thank the organizers for inviting me to this interesting meeting. I will be presenting my talk in the style of theoretical physics, which is different from what we have heard until now. No surprise, because the primary commitment of mathematics is with logic, whereas the primary commitment of theoretical physics is nature. So this difference makes important differences in the style. Whereas mathematicians do not like to state things they have not proved, this happens all the time in theoretical physics. This said, let me show to you these lines by Enrico Fermi in his book of Thermodynamics, 1936. He says the entropy of a system composed of several parts is very often equal to the sum of the entropies of all the parts. An intelligent man like Enrico Fermi, he wouldn't write very often just like that. He surely had something in his mind. He had counterexamples. He had something specific for writing very often and not always. And in fact, he touches a little bit on those counterexamples, but he adds, these conditions are not quite obvious, and in some cases, they may not be fulfilled. This is precisely the content of my talk. I'm going to talk when this kind of thing is not fulfilled. When it is not fulfilled, Fermi adds, it can play a considerable role. So here you have a little table of entropies. At this line, you have Boltzmann, Gibbs, von Neumann, Shannon, entropy. It's essentially the same thing. It's a logarithmic measure of the lack of knowledge that the observer has on the system. And here you have the simplest expression, minus sum of p log p. When the probabilities are all the same, this gives you this expression, which is on the gravestone of Ludwig Boltzmann in the Central Cemetery in Vienna. Fine. But I'm going to talk mainly about this line, and you see immediately that in this line there is an extra index, q. If in this line you take q going to 1, you get this line. So I'm not exactly talking about an alternative, I'm talking about a generalization, since for the case q equal 1, we recover the usual entropy, and therefore we recover the usual statistical mechanics. This expression and this expression have a lot of common features that I will not describe in detail now, but you have a list of them here. They are concave, they can be extensive, they are less stable, a lot of things. But of course, they must differ in something, because the only thing that differs in nothing is sum of p log p, and you don't generalize. So when you do a generalization in whatever field, you violate at least one property of what is being generalized. The property we are going to generalize is precisely the one that was pointed by Fermi. This expression is additive, and I will come back on to that word, whereas that one is non-additive. And I will tell you what are the consequences of this. Let me introduce this function, q logarithm of x, defined like this. And when you take the limit q going to 1, this becomes the normal logarithm. Here you have the inverse function of this, and we will call it q exponential. And again, when you take q going to 1, you recover the usual exponential. If instead of x, if you put minus x squared, we will call that a q Gaussian. And a q Gaussian, when q goes to 1, yields a Gaussian. Okay. These functions appear all the time in the theory I'm going to talk to you about. And in particular, the table that I just showed to you can be rewritten in a more compact, more elegant way by using this. So here you have log, log, q log, q log. Now about SQ. There is a long story about the definition of this entropic functional, but a question that arises easily is, are there senses in which SQ is unique? Many. There is the Santos theorem, there is the Abbe theorem, there is Topsoe factorizability in game theory, there is Amari and collaborators conformally invariant geometry. This is from the people from Budapest, thermostat universal independence. And the most recent one is the Enciso-Tempesta theorem. These two are from Madrid. And I will concentrate a little bit onto that. See. Hello? Yes. So let me focus on the last one. An entropic functional is trace form if it can be written as the sum of a function of the probabilities. A nice function, but a quite generic function. If it is so, you can define a generalized logarithm, and this quantity that you see here, you can call it generalized surprise or generalized unexpectedness. So this quantity has the following property. If the probability is equal to 1, the surprise is 0. So if I leave this, we all know it's going down. So if I leave it and it goes down, we have no surprise. So surprise is 0. On the other hand, if I buy a ticket of the lottery, I know the probability is going to be almost 0. It's not 0, but it is almost 0. If I win the lottery, which is possible, then you're going to have an infinite surprise. So this concept plays an important role in the understanding, in the intuition of what is entropy. So trace form allows you to define a generalized surprise. The second property, which is interesting, is composability. So if an entropy is such that it can be a function of the separate entropies, SA and SB, A and B being two independent systems, if it is so, it will be said composable. This is basically the origin of the nutritionist that says, if you eat an ice cream of 100 calories and you eat a steak of 200 calories, then you're going to get inside 300 calories, the sum. And the nutritionist does not know much about quantum mechanics and quantum chemistry and the calories involved in the various molecules of an ice cream or of a steak. But he or she knows how to do 100 plus 200. That gives you 300. So this is a basic requirement if you want to fit issues from thermodynamics. So this function has to be such that for a particular case it is the sum, which is the example that I just told you, just the sum. If one of them has no calories, then what is left is the calories of the other one. It is commutable and it is associative. So this function phi has to satisfy this kind of properties. And the theorem by Enciso and Tempesta consists that the unique entropic functional, which is simultaneously trace-form, composable, and contains Boltzmann entropy as a particular case, is SQ. So here you have the same in a diagram. Here you have the trace-form entropies. Here you have composable entropies, a lot. Here you have another set of entropies, which include SBG as a particular case. Here you have a strange, a bizarre entropic functional, which violates all these three properties. But in fact, the only entropy which is in this intersection triangle in the middle is SQ, which contains Boltzmann entropy as a particular case. Now, let me talk about the word that I used, additivity and also extensivity. By following the definition of Oliver Penrose, the brother of Roger Penrose, Foundations of Statistical Mechanics in 1970, he said that an entropy is additive if, for any two probabilistically independent systems A and B, the entropy of the sum equals the sum of the entropy. If this is violated, then the entropy is non-additive. You can prove in 2 lines that SQ satisfies this, and therefore SQ is non-additive unless Q equals 1, where this cross term disappears. If you cancel here K, 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 you have this. And this is interesting to mention that Q equal 1 plays the same role as the Boltzmann constant going to infinity. So these two situations are basically the same. They lead to additivity because this term disappears. And I will come back onto this Boltzmann constant that you see here. Extensivity is a very different thing. If you have an entropic functional, in 15 minutes, you will know if it is additive or not. But if you have the same entropic functional and a specific system, it might take you 15 years to know whether it is extensive or not. Because the question that is posed here is not only about the entropic functional, but the system on which it is applied. And if the system has wild correlations, wild elements, if it is a mess, then answering whether that entropy is extensive or not might be also a mess. And what's the definition of extensivity? That the entropy of n elements is proportional to the number of elements. Or the entropy of n degrees of freedom is proportional to the number of degrees of freedom. Extensivity in the thermodynamical sense. Now, let me show you through examples the big difference between additivity and extensivity. So I will call W the total number of possibilities with non-zero probabilities, and we will assume that those possibilities are equally probable for simplicity. So if W of n increases exponentially with n, for example, n coins, where you will have 2 power n, then you better use Boltzmann entropy, because the logarithm of this is proportional to n, and that's perfect because this is extensive as required by thermodynamics. But if instead of have that, if you have a complex system like that one, if you use Boltzmann expression, which is the logarithm of W, this is going to be proportional to the logarithm of n. We don't want logarithm of n. We want n, which can be terribly different from logarithm of n, in particular if n is the Avogadro number. But if you use SQ with Q equal 1 minus 1 divided by rho, the same rho that you see here, that one is extensive. Oh, fine. Now, you can have 1 million different families. You can have that one, the stretch exponential family. There is no value of Q that can make this to be extensive. Then what do? Well, you change the entropic function. And there are in the literature entropic functions such as they called S delta, which when delta equals 1 divided by gamma, the same gamma that you see here, it is extensive. That's fine. And another important family, W can increase as the logarithm of n, slowly with n. Then none of the previous yields extensivity, and we want extensivity. So you have to define a new entropy. Curado from CBPF defined such an entropy, and his entropy when lambda is equal to 1 divided by d, the same d that you have here, it is extensive. Now, a remark is that this number, when n is very large, is much larger than this, which is much larger than this, which is much larger than this. But what is this? This is basically a positive Lebesgue measure of the system. Mu times mu, mu times mu times mu times mu. So you are occupying with a positive Lebesgue measure the phase space of the system. And all these yield 0 Lebesgue measure. So the phase space appears in these complex systems to be occupied very little in very important positions, in very important points. But the Lebesgue measure is going to be 0. And that changes everything, as you will see. What I just said is summarized in this table. Here you have Boltzmann entropy, which is additive, SQ, which is non-additive, S delta, which is non-additive, S Curado lambda, which is non-additive, and as you saw in that diagram, there are about 50 different entropic functionals in the literature. There were 1 or 2. Today there are 50. So if you have this family, like the coins, you better use that one because it is extensive. And you should not use SQ, S delta, and that one. If you have this family, you better use this because it is extensive. If you have this family, you better use that one because it is extensive. If you have this, the same. So, if you married Boltzmann, you will stay here until the death separates you. But let me tell you that there is a better marriage, that one. Thermodynamics or Clausius. And what are we doing there? Let me make an analog with mechanics. So the composition of velocities in Galileo is just the sum. So you go 100 kilometers on a train, 100 kilometers per hour on a train, and on the train you walk at 10 kilometers per hour, then with respect to the land, you are going to 110. You can do it by heart, by heart, yeah. 100 plus 10, that's it. But in relativity, it's a mess. It is this. In the Lobachevsky space of velocities, it's not the sum, it's this. So why Einstein sacrificed such a beautiful additive law because he had a superior goal. He wanted to unify mechanics and electromagnetism, the Maxwell equations that Martin was discussing for you 1 hour ago. And therefore, he considered that getting from this to this was a small price to pay if you want to unify electromagnetism and mechanics. And this is what he did. So this can be considered as a sort of metaphor of what we are doing here, because we are sacrificing the additivity, the simple additivity of Boltzmann entropic functional, because we have a superior goal. We want not to violate thermodynamics, very specifically the Legendre structure of thermodynamics. We have no reason for wanting to violate thermodynamics, where, as you will see, we have dozens and dozens of reasons for wanting to violate additivity of Boltzmann entropy. Well, you see, here you have an illustration of the same idea. Euclid's set of axioms, including his celebrated fifth postulate, yields the magnificent Euclidean geometry. When you violate this postulate, you get Riemannian geometry. So one can say, if we stubbornly insist that the fifth postulate was not proposed by Euclid, but was instead mandated by God, general relativity would not exist. So there are many occasions in which it is interesting to violate something. And I repeat, we are aware of no reason for wanting to violate thermodynamics. So violate whatever is necessary for not violating thermodynamics. Now, about the constants. Here you have four fundamental constants: Planck constant, Newton constant, velocity of light, and Boltzmann constant. With these four, Planck defined this quantity: Planck length, Planck mass, Planck time, Planck temperature. So they play a very important role in physics, and I have had wonderful discussions with Michael Duff from Imperial College that you might know. And so if the 1 divided by c is different from 0, you go from Newtonian mechanics to special relativity. You do so whatever is the value of c, of 1 divided by c, as soon as it is different from 0. Because you go from Galileo transformation to Lorentz transformation. If g is different from 0, you go from special relativity to general relativity, because there is the emergence of curvature of space-time. If you take Planck constant different from 0, whatever value, you go from Newtonian mechanics to quantum mechanics, which means that not all physical observables can be simultaneously known. And finally, when this is different from 0, you go from Boltzmann-Gibbs statistical mechanics to non-extensive statistical mechanics, which is what I'm talking about right now. For any value of this different from 0, you are essentially not here, but you are here, because you have the emergence of entropic non-additivity. Well, no, sorry, here. Now a question appears: where Q comes from? How can I calculate Q from first principles? Not from fitting, but from first principles, where it comes from the very basic electromagnetism and mechanics. It can be classical mechanics, it can be quantum mechanics, like this example, it can be relativistic mechanics, it can be quantum chromodynamics, but at that level, you calculate Q if you can. It was possible to do that calculation some years ago with Filippo Caruso, who at the time was at the Scuola Normale Superiore in Pisa. And we obtained for systems in one-dimensional systems, a quantum phase transition at 0 temperature, we obtained at the critical point the expression of Q. Here you have it. C here is not the velocity of light, but it is what in quantum field theory is called the central charge. So here you have the plot, Q as a function of the inverse of the central charge, and you have a full line with Ising model, with a transverse field here, X, Y, etc., etc. And here, when the central charge diverges, you go back to Boltzmann. So this is a beautiful illustration of what I told you. We are not proposing an alternative. We are proposing a generalization. And therefore, the point Boltzmann gives should be here, and it is. Let me tell you about a first principle calculation of another system. So here you have the famous logistic map, a one-dimensional dissipative system, and as a function of this parameter R or A that I will use right in the next slide, you have the most chaotic position, which is at the end, where the Lyapunov exponent is logarithm of 2, which is different from 0. And you have another special point here, which is the edge of chaos, between chaos and regular orbits, and which sometimes is referred as the Feigenbaum point, where the Lyapunov exponent is 0. So let me analyze these two situations, this situation and this situation. So A equal to here is the extreme value for strong chaos. The Lyapunov exponent is positive, and if you calculate the entropy as a function of time, starting from initial conditions where all the initial conditions are in a little window in the phase space, and therefore it starts with entropy equals 0, because you know it's in a little window. And from then on, you allow the system to evolve and the entropy expands because the system starts going everywhere. So if you take Q equal 1, you have a straight line. And when W increases more and more, the straight line increases more and more. And at the end, you have a mathematical limit on which I will talk a little bit. If you take Q equals 0.8, it's not a straight line. If you take Q above 1, it's not a straight line. Q equal 1 is the very special value for which this business gives you a straight line. And why do you want a straight line here? Well, because, first of all, straight lines are so beautiful, right? And second, because we want to have a production of entropy per unit time finite. So this means a straight line. In mathematics, at IMPA, they use all the time Shannon entropy, which is Boltzmann entropy, and they calculate a lot of things. What I'm showing to you, why that Q equal 1 is special, and it is the correct to be used for this system where when the Lyapunov exponent is positive. Here, you have the same basically figure that I showed to you that was prepared with Ernesto Borges from Salvador Bahia. And you have the entropy, the average value, as a function of time. And you have here the straight line being higher and higher when W is higher and higher. The first remark that we can have on this is that if you scale this by logarithm of W, and the same here, all these curves collapse into a single figure, And in this region is where you have the straight line. Now, this has to do with the so-called Pesin identity. The slope of that straight line is called K, which means production of entropy per unit time. And the identity of Pesin says that under quite generic conditions, it's equal to the Lyapunov exponent. And you verify that in the figure that I just showed to you, the slope is 0.69, which is logarithm of 2. Okay, and I remind you the expression of the sensitivity to the initial conditions for such a case is the exponential of the Lyapunov exponent time multiplied by time. So it's a very wild loss of information when you have strong chaos. Now, what happens if you plot? Yeah, first of all, I should show to you something. Oh my God. You don't see it here because it's very small, but here there is a maximum. All these curves have a little maximum, which means that on the right, the entropy is decreasing. Normally people, when you say, I have a system whose entropy is decreasing, people say, what about the second principle of thermodynamics, which says that the entropy should increase and yours is decreasing? What about that? Well, the second principle of thermodynamics talks about systems that are very large, etc., which is not the case here, which are isolated, which is not the case here because this map is dissipative. But if you divide this height by the height of the stationary state, is slightly above 1, right? Because there is a maximum. And it turns out to be like this. This is the ratio of the maximum to the value of the stationary state when W goes to infinity here. So it goes like this, and it goes practically to 1. We have the numerical evidence. We don't have the proof. So I would like one of you to provide the proof that this limit, when W goes to infinity, goes precisely to 1, like in the second principle of thermodynamics, where the entropy never decreases. Well, this is what happens at that final point, not at the Feigenbaum point. At the Feigenbaum point, the Lyapunov exponent is 0, and Q can be calculated from first principles. And here you have it with 1018 digits. It was possible to calculate this because with Marcelo Lira from Maceió, we established this connection between Q and the Feigenbaum universal constant alpha. And some young German calculated this with 1000 digits. So we put in here and we have Q with 1000 digits. It's clear this is not a fitting. Somebody who would be able to fit something with 1000 meaningful digits would deserve not one but half a dozen of Nobel Prizes or Fields medal. So 0.24, what happens for that value of Q? The same structure that you saw before. If you put SQ as a function of time, for that value, you get a straight line. If you put Q below, it bends upwards. If you put above, like Q equal 0.5 or Q equal 1, it bends towards down. So if you put that one, you have a straight line. You have a finite entropy production per unit time. It has been shown, and in some little cases, it has been mathematically proved that Peasant identity can be Q generalized. And you have KQ, which is the slope that I just showed to you, equal to the lambda Q, which is the Q generalized Lyapunov exponent, through this expression. The sensitivity is not the exponential of time, but it is the Q exponential with Q equals 0.2445, lambda Q time. This lambda that appears here is the same that appears in the slope that I just showed you. Here you have how it behaves. The entropy SQ for Q equals 0.2445 as a function of time, because it's very slow, it's a complex system, its dynamics is slow. So we better plot it as a function of the logarithm of time. So here you have a maximum, and here you have the stationary state. You remember in the case of strong chaos, the difference between the maximum and the stationary state was almost nothing, 0.01, something like this. Here it's huge. Look the height here and look here. I'm going to show to you again the height divided by this. Let me show it here. The ratio as a function of 1 divided Q logarithm of W. When W goes to infinity, this goes to 0. When this goes to 0, the ratio seems to diverge or to go something very high. In fact, if you plot here the same data, not in linear scale, but in logarithmic scale, you have this. And therefore, W going to 0 is far away here. And you see, it tends to be more than exponentially increasing. So this probably diverges. Again, we have this strong indication. We don't have the proof. It would be very nice if one of you could prove that at the Feigenbaum point, where the attractor is a multifractal, and this is why in one of your talks I asked you, can you say something about fractals or multifractals? That was the reason of my question. So in that point, you have a sort of huge violation of what some people might think of the second principle of thermodynamics, because it decreases very strongly as a function of time. Here you have another dissipative system where it has been possible to calculate the value of Q from first principle. As I told you, it is always determined by first principles, electromagnetism, mechanics, whatever mechanics, but you rarely can do the calculation. Well, in this case, it was possible to do the calculation, and for overdamped motion of the vortices in type 2 superconductors, it turns out to be Q equals 0. This is a Q Gaussian with Q equals 0. This is not a Gaussian, which is Q equals 1. It is a Q Gaussian. And there is another system. I will not enter into details. A couple of years ago, in fact, 4 years ago, it was also possible to calculate Q from first principles, and it is this line here. And these two systems have this point in common. So I'm showing to you examples where Q can be calculated from first principle. The two examples that I showed to you were dissipative systems. Let me show to you a conservative system. So this is due to a collaboration between Tirnakli from Turkey and Borges from Brazil. And they analyzed the standard map. So the standard map introduced by Chirikov long ago, it only has one parameter, K. And if K is very big, this two-dimensional map is very chaotic. If K is very small, it has a nice orbit, which depends on the initial condition. That was in a torus, and we heard several times during this conference that the torus are more nice for proving things. Well, this is on a torus. And if you take K very large, for example, 10, and you check the central limit theorem, it yields a Gaussian. This is the analytical Gaussian, the dashed line, and the green points are the numerical results. This is a log linear scale, and therefore you see a parabola, which is a Gaussian. When K is large, this is the intuition that Boltzmann had surely in his mind when he invented statistical mechanics, and in particular, he proposed the molecular chaos hypothesis, is this business. But when K is small, for example, 0.2, the system does not like Gaussian. It likes this. This is not a Gaussian at all. This is, in fact, appears to be a Q Gaussian, with Q equal 1.935, and they worked a lot of tricks to find out what would be the exact number here. And finally, after 5 years, they published these results. 3 mathematicians came interested into exactly this problem, and they could prove that for K equals 0, Q equals 2. So the exact answer is not 1.9, it is Q equals 2. Oh my God. May I make a suggestion? Ele não fa... Posso fazer uma sugestão para a rica universidade da Unicamp? Comprem um bicho desses que coloca aqui e terminam o problema. So here you have the exact answer for K equals 0, and it is not K equal 1, it's K equal 2, which is a Cauchy distribution. Physicists call it a Lorentz distribution. I call it Cauchy-Lorentz distribution, so everybody is satisfied. It's not a Gaussian. So here, the central limit theorem does not work, but here it works. Now, it has been introduced in all this theory. I'm giving you some flashes of the theory, because the whole thing would be very long. But here you have a generalization of the product. This is called the Q product. And the expression is given by this. And this object, when you take Q going to 1, recovers the usual product. And also, it is commutative. It has extensivity. The Q logarithm of the Q product of x plus x times y is the sum of the Q logarithms. And remember, the Q logarithm was the entropy. So this is basically extensivity. But if you apply the Q logarithm to the normal product, you get an extra term, which is the violation of additivity. It has all these properties. It is associative. It has a unit. It has a zero. And most important in this story is that it is distributive. The Q product is distributive with regard to a Q generalized sum, which is expressed here. And when you take Q going to 1, the Q generalized sum becomes x plus y. This is a result by 2 people from Salvador, Borges and Costa. And this is kind of the seed for generalizing the concept of vector space in a nonlinear scheme, because all this is nonlinear, but it has the basic algebras that might be able to yield a nonlinear Q generalized vector space, which would be very convenient, in particular for theoretical chemistry. If I want here, if I want what? Here. Yeah. Well, it is distributive. There is a mistake here. Oh, yeah, absolutely. Yes, you're right. Here it should be the Q plus. Yeah, you're right. I'm going to correct it. Where the Q plus is defined like this. Yes, thank you. With this structure of the Q product, it was possible to generalize the central limit theorem and the Levi-Gnegienko's central limit theorem. That was done with co-authorship of two mathematicians from United States and the mythical Murray Gell-Mann, the Nobel Prize, who died 3 years ago, and who invented the word quark. So his car has the matriculation a big quark. And he was called in his neighborhood, oh yeah, that's the quark guy. Well, that was Murray Gell-Mann. Well, we generalized these two theorems. I'm not going to enter into any details, but I'm going to show to you this scheme. If you have Q equal 1, this is to say basically IID or almost, if the variance is finite, the attractor is a Gaussian. And that's the classical central limit theorem. If the variance diverges on some other mathematical delicacies, the attractor is Levy distribution. So these two are in any reasonably good book of probabilities. The two theorems that I was referring to are these two. And here, if Q is different from 1, so in the presence of a wide class of strong correlations, the attractor is not a Gaussian anymore. It's a Q Gaussian. And here is what we call the Q alpha stable distribution. That one contains this and this and this as particular case. This contains Levy distributions as particular case. So let me now tell you about statistical mechanics, Boltzmann-Gibbs statistical mechanics. In the book of Gibbs, 1902, Elementary Principles in Statistical Mechanics, he says, in treating of the canonical distribution, we shall always suppose the multiple integral in equation 92 to be finite. The equation 92 is what today we call partition function. A couple of times appeared partition functions here in the blackboard. So he says, we are going to suppose that it has a finite value for the partition function, as otherwise the coefficient of probability vanishes and the law of distribution becomes illusory. What law of distribution? His law of distribution. Gibbs is writing that his and Boltzmann law of distribution, the celebrated Boltzmann weight or Boltzmann-Gibbs factor, is illusory if the partition function diverges. So they knew that, but thousands and thousands of physicists in their courses forgot that, and they were putting Gibbs distribution from heaven like if it was mandated by God. And now you see why I asked you why you were using an exponential measure in one of your examples. I was thinking about this. Genius of Gibbs was so impressive that he even gave a physical system as a counterexample. And his system is Newtonian gravitation. He says contains materials points which attract one each other inversely as the square of these distances. Here, for gravitation, Boltzmann-Gibbs statistical mechanics does not work. And well, these are very important lines. Here you have an interaction, a two-bond interaction, which could decay as an inverse of distance with A being positive, and therefore I am considering an attractive potential, which decays with an alpha, which can be 0 or positive. And this quantity is integrable if alpha divided by d is above 1, It is non-integrable when alpha divided by d is above or equal to 0 and below or equal 1. In equal 1, this non-integrability introduces logarithmic corrections. And this is why I asked, could the d equal 4 case that you have there, could it be handled if you had logarithmic corrections? This is precisely what happens along this line where alpha equals d. So in this plot, here you have Newtonian gravitation, d equals 3, alpha equals 1. Here you have dipole monopole, which is the tides in the sea, dipole, dipole. And the air in this room is basically Lennard-Jones interaction, which has alpha equals 6. So the air in this room is d equals 3 and alpha equals 6 up there. And it is in the region extensive, where you must use Boltzmann-Gibbs statistical mechanics and Boltzmann entropy, Boltzmann-Gibbs, Shannon, von Neumann entropy. But I'm talking about this region, which is the hard region where this theory fails. And here you have this recent paper 4 years ago, Validity and Failure of the Boltzmann Weight. This was done in collaboration with a student at CBPF, Antonio Rodriguez from Madrid, Fernando Nobre and myself from CBPF. And here you have, for the XY model, planar rotators in d dimensions, here you have in log linear scale the distribution of momenta, or if you prefer, the distribution of velocities. And alpha divided by d is 0.9. It's below 1. It's the region where the potential is not integrable, etc., where we expect Boltzmann-Gibbs to fail. And it does. Look at this. This is a Maxwellian distribution. This is a Gaussian. The system does not like it. The system likes this. When I say the system, these calculations have been done from first principles. The only thing that we have used here is force equal mass time acceleration. That's it, because it's classical mechanics. And a huge computer, and a very clever student to handle all this. So from first principles, the system does not like Gaussians, does not like Maxwellian distributions, which are declared with big glory in all the books of statistical mechanics, which is fine as long as they also say it is because you have short-range interactions. If you have long-range interactions, it doesn't work, but they don't declare anything. They put it as if it was always, and it is not. Here, even worse, the distribution of velocities is one of the landmarks of Boltzmann-Gibbs statistical mechanics. But it is the heart of classical statistical mechanics, which is the weight of Boltzmann-Gibbs, the distribution of energies. It fails. It doesn't like the Boltzmann weight. Here you have Q equal 1. It doesn't like it. It likes this. And this is roughly a Q Gaussian with Q equal 1.3. From first principles, it doesn't like Boltzmann-Gibbs weight, which is the heart of the normal statistical mechanics. Another example, Fermi-Pasta-Ulam model with long-range interactions. This was done in collaboration with two mathematicians, Tassos Puntis and Eleni Christodoulidi. And you have, sorry, no, the other way around. And you have this picture which emerges. It is done in the computer by using force equal mass time acceleration, nothing else. And here you have 1 divided by n, the number of particles, 1 divided time to some positive exponent, which is time, and depending on whether you come to 0, 0, which is your mathematical limit, when you have thermodynamically big system and stationary state, you want to arrive to this point, you can arrive from this way and you can arrive from that way. And therefore inverting the limits n going to infinity and time going to infinity, you might have different results. This is why I put a couple of days ago a question to Claudio Landim, who, well, he's not here, but here he said, you put me that question many years ago. Well, you see here a realization of this difference, of the difference of limits. Now, I told you theoretical physics, primary compromise is with nature. So all this is very nice, but a theoretical physicist is only happy when nature says, I like your theory, the experiment. So this is an experimental work done by people from France and one Brazilian. And they published this paper in 2015, where they verified this scaling law that a young man from Netherlands and myself had predicted 19 years before. We predicted this law in 1996, and it was verified a few years ago in France. And this is the experimental data, and one is the theoretical prediction. And the error, the experimental error they declare is 2%. So within an error of 2%, they verify this prediction that was advanced 19 years earlier. Another experimental evidence. Here you have at CERN, the LHC, collisions proton-proton at huge velocities, almost the velocity of light. And they collide, they form a quark-gluon soup, a mess, a big mess. This soup tries to relax, and while relaxing, it emits hadrons. And they measure the longitudinal and transverse momenta of the hadronic jets. And here you have in log the distribution of transverse momenta. And the points are experimental data in 1, 2, 3, 4, 5 different detectors, conditions, etc., etc. And the lines are this very simple Q exponential of minus the energy divided by temperature. So here, there are several remarkable things, but the first is the talent of these experimentalists that are able to measure in a single experiment with 5 different detectors, 14 decades, 10 power 1, 10 power minus 14. 14 experimental decays in a single experiment. That means that they are capable of controlling their experiment with precision 0.0000014 zeros and a 1. Very impressive. Every time I see this, I become impressed again. A second very impressive thing, all these data are well fitted by this simple Q exponential, where Q is 1.14 and the temperature is 0.13 JeV, which is the mass of the pions, which is involved in all this, and whose existence was found many decades ago by Cesar Lattes and from Campinas and from CBPF. He was the founder of CBPF and collaborators. He didn't win the Nobel Prize, but he deserved it. So the temperature that appears here is precisely the mass of the pion, of the pions. Now, remember this, 1.14. Now you have a different result. 20 years ago, Rafelsky and his student at that time, Brian Walton, in Arizona, they made a calculation with a quark gluon soup. And they found that the diffusion of the charm quark, which is one of the heavy quarks, was not Q equal 1, was not normal diffusion, was Q equal 1.11, which is anomalous diffusion. They found this, and during 20 years, nobody did nothing with that. But then, coming to the game, two Brazilian, Ayrton Deppmann from São Paulo and Deborah Menezes from Santa Catarina. Today, she is the president of the Brazilian Physical Society. And this guy from Spain. And they calculated within a Young-Mills field theory by using the one loop approximation in the Wilson loops that we were discussing today, the quantum chromodynamics. They calculated from first principles Q, which I told you is very hard to calculate, but they succeeded. And here you have their answer. 1 divided Q minus 1 is this. NC is the number of colors of the quarks, and F is the number of flavors of the quarks. And if you put SU3, that was mentioned several times, you have 3 colors and 6 flavors, you get Q equal 8 divided by 7. And if instead of SU2, you use SU2, Q becomes, which is 1.11, doubly fantastic. So, 2 theoretical explanations of 2 results that were in the literature since long. This kind of things appears in all kinds of systems, and it appears also in transport of phenomena, like the Newton law of viscosity, 17th century, Fourier law for heat conduction, Ohm's law for charge conduction, Fick's law for diffusion. And I will concentrate onto this because we were able to calculate with these people, a student of mine in CBPF, Tirnakli from Turkey, Deniz Eroglu from Istanbul. And we calculated using force equal mass time acceleration from first principle again, and we could obtain the thermal conductivity as a function of temperature. Here you have 3 different sizes which can be collapsed in a unique curve here for 1 dimension, the same in 2 dimensions, the same in 3 dimensions. And when you discuss this, it turns out to be not a Q Gaussian, but a Q stretch exponential. It's not temperature to the square, but temperature to a power, eta, which depends on dimension. If eta was 2, this would be a Q Gaussian, but eta is different from 2. If in this expression you consider the system of large systems, this is to say L, the size, going to infinity, and therefore we are going from the microscopic world to the macroscopic world, L going to infinity, which is what had in his mind Fourier in the 19th century, when many physicists even doubted where atoms exist. So his prediction was for macroscopic systems. And these results give you this, which means that this exponent is 1, 2, 3 for d equal 1, 2, 3. And therefore, Fourier law is satisfied from first principles in 1, 2, 3 systems, in 1, 2, 3 dimensions for this system. This proof is not in the mathematical sense. It's a numerical strong evidence. It's not a proof. Up to you to provide a proof about that. I won't enter into any details here, but just for you to know that these non-additive, extensive entropies enable to calculate many things, and for example, cosmological issues. And these were done with a young Argentinian, Zamora. He did a postdoc in CBPF. He did 3 beautiful works. 2 of them are these. And as it happens, unfortunately, too often in Latin America, the postdoc finished, he went back to Argentina, and he is at his home without job. Maybe you want to give him a job at Imperial College. So here are the cosmological results. I just want to mention this, where this region here is the dark energy stage, where apparently we are nowadays in the universe. You can establish connections between these entropies and complex networks. I will not enter into the details, but you have networks like that one, which appear in the web network, in authorship networks, in neurological networks. And you can define an energy by adding the width of these things. This, here you see it. This plus this plus this plus this. These different widths summed, divided by 2 for not having double counting. You can call that energy. And you can see that the distribution of these energies is a Q exponential, which yields, here you have Q as a function of the range of the connections. Here you have a nice plot. And this makes one to think about possible connections between random geometric problems and statistical mechanics. And let me show to you 3 famous such connections in Boltzmann-Gibbs statistical mechanics. The Castellano-Fortuin theorem. When you take the number of states of the Potts ferromagnet going to 1, it's isomorphic to bond percolation. A second example, when you take the same thing with the number of states of Potts ferromagnet going to 0, it's isomorphic to random resistors. And the third example is the Gen isomorphism, when you consider the limit n going to 0, when n is the UN geometry that was mentioned more than once. This limit is very strange. It's a vector that has 0 components. What about that? So, in fact, it's an analytical extension. When you take this limit, you get the self-avoiding random walk, which is a polymer cannot go back where it already passed. This is a terribly non-Markovian process. The polymer is growing, and 1,000 years later, he knows that he cannot pass here, where he passed 1 million years ago. So it's very, very non-Markovian. Well, De Gennes proved that it is isomorphic to this, and he won the Nobel Prize of Physics, mainly because of this connection. So here, in this paper that appeared a couple of months ago, we established a similar connection. I will not enter into details, but a connection of a random network, which is a geometrical random problem, with this Q exponential, and Q is 4/3 and beta is 10/3, we are almost sure that it is like this, but we will be sure when one of you will prove in the style of mathematics that this is so. Finally, these things, amazingly enough, have a lot of medical applications. And here you have a very recent contribution coming from Islam, that one, from Iraq and Malaysia. 4 engineers, they analyzed a section, a computer tomography of people with COVID-19. And here you have the 2 lungs, and here you have a severe fibrosis. If you handle the same data with Q equals 0.5, you get this. Any doctor would prefer to make a diagnosis with this picture instead of this picture. Second patient, here you have the fibrosis. When you put Q equals 0.5, you get all these details. Third patient, here you have the fibrosis. Here you have what you obtain for the same data using Q equals 0.5. So entropy can play all kinds of jobs, and this is an interesting job. I would like to finish by summarizing some open mathematical challenges. I'm almost sure these things are correct, but I don't know how to prove it. And maybe you can prove one or the other. It concerns the generalized central limit theorem, necessary and sufficient conditions outside Gaussians. For example, Q Gaussians. The generalized large deviation theory, we heard a talk yesterday about this. Outside exponentials. And for any value of Q here is proportional to n. This fact that it is proportional to n, not only for Q equal 1, but for Q different from 1, is directly related to the fact that the total entropy, this is the relative entropy per unit particle, multiplied by n is the total entropy. The total entropy is extensive. Either Q equal 1 or Q different from 1, thermodynamics must be satisfied. The generalized Pesin identity, accepting a couple of examples, we don't know how to prove this, but we practically know that it is correct. Generalized vector space, I mentioned to you. The ratio of the height of this entropy as a function of time, when W goes to infinity, at points where the logistic map has a positive Lyapunov exponent, this ratio, this limit, appears to be 1. When you are at the Feigenbaum point, this limit appears to be infinity. We are almost convinced that it is so. We will be absolutely convinced when one of you will prove this. And the isomorphism that I just mentioned also is an open mathematical challenge. The random geometry and the connection with Q statistics through this distribution where Q equal 4/3 and beta equal 10/3. And finishing, let me show to you a couple, three months ago, with a mathematician from the United States, Sabir Umarov. We published this paper, this book, Mathematical Foundations of Non-Extensive Statistical Mechanics. And some of the things that I have shown to you are included in this book. This said, thank you.
So, questions, comments?
Thanks for the talk. Can you comment a bit on what you mean with the generalized large deviation theory? Because I mean, what kind of systems do you have in mind? Because of course there are already examples where the behavior is not exponential, but maybe stretched exponential.
Systems with, in spite of, because yes, systems which, because of the strong correlations between their elements, they violate the usual central limit theorem, and they satisfy a Q generalized central limit theorem, because we verify in several examples that the attractor is a Q Gaussian. So when the attractor is a Q Gaussian, the large deviation probability appears to be a Q exponential, not with the same Q, with a Q which is a function of the previous one, such that when the previous one is 1, and you have Gaussians, the normal central limit, that Q of the large deviation theory is also 1. So Gaussians gives you exponentials. Q Gaussians gives you Q prime exponentials. And these Q prime exponentials, in all the examples, the exponent of the Q prime exponential is proportional to something which appears to be like a Q generalized relative entropy per particle multiplied by n. And therefore, the total entropy is extensive. In all the cases, I was afraid of violating Legendre's structure of thermodynamics, and all these examples show that it is not violated, which makes me very happy.
Okay, thanks a lot.
Any further questions? So let's thank again Professor Constantino Salles. Thank you very much.
Ready? Okay, so we come to the last talk of the day of Gabriel Apolinario, which is about a dynamical model of the turbulent energy cascade. So, go ahead.
I'd like to thank the organizers for the opportunity of giving this talk. I'm going to describe the work I've been doing over the last 2 years in my at the ENS de Lyon with Laurent Cheviard, which is at the physics department at the ENS de Lyon, and with Jean-Christophe Morat, which is at the math department at the same university. And I'm going to describe a model for turbulent cascades. So first, I'm going to begin with some of the phenomenology of turbulence, some of the phenomena which we observe in simulations and in experiments in turbulence. To begin with, these are the Navier-Stokes equations. So they describe turbulence when doing experiments in fluids and air or water. We observe turbulence at small Reynolds numbers. These correspond to small viscosities. And when doing experiments and numerical simulations, we observe random behavior, behavior which is strongly spreads energy through all directions and spreads matter. And this is roughly what we call turbulence when we run experiments and do numerical simulations. They happen in these equations, the Navier-Stokes equations, which describe the evolution of a 3D velocity field U, defined in 3 dimensions and in time. And as we add an external forcing, and we have incompressibility in the velocity field, and as we reduce the viscosity, as nu goes to 0, we observe strongly random and intermittent behavior, as you see what that means. And we can observe in numerical simulations, so these are 3D simulations, 2D slice of 3D simulations. This is one component of the velocity field, and we observe that energy is injected at the large scales through the forcing F. So F injects energy at the large scales, and through the dynamics of the Navier-Stokes equations, energy is redistributed to the small scales. So here we see structures both at the large scales and the big green and big dark blue regions, and we also observe structures at very small scales, such as the swirls and vortices that appear everywhere. And so this is one of the basic phenomena which is observed in turbulence, this redistribution of energy from the large scales, where it is injected, to the small scales, where it manifests this complicated behavior. If we look at a one-dimensional section, so this is one component of the velocity field along a one-dimensional line, straight line, we also observe a rough behavior, as in the rough velocity fields we have seen over the course in this school and over the last week. So we would like to describe this as some velocity field that shares properties similar to these random velocity fields. So let's go back again to this 2D slice of 3D simulations. The basic of observable we consider when trying to characterize the roughness of this velocity field and the statistical properties of it are increments in velocity. So we measure the velocity at one point, at R2 and at R1, consider the difference between the velocities at these 2 points. These two velocity fields are separated by a distance L, and we would like to know how the moments of this increment, the statistical moments of this increment, behave with L at small scales. So, and what we observe is that this describes rough fields, rough turbulent velocity fields. So again, this is an increment in velocity, delta L, at the scale, separation at a scale L of the velocity field U. And we look at it experimentally and numerically at its statistical behavior. So, and what we observe is that its second order moment behaves as a power law in L, which is the separation between these two vectors, with an exponent 2h, where h is roughly 1/3, the value we obtained from the Navier-Stokes equations. And this already characterizes the rough behavior of these random velocity fields. We will also measure higher order moments. So these are in general called structure functions of order 2 in this case, of order q, if we change this value from 2 to q. And they all show some power law behavior in L with different exponents. So what Kolmogorov conjectured in 1941 is that in general, these structure function exponents could be described as power laws with linear exponents. So h is the same, and we'd have a linear behavior in Q. So this was conjectured as an approximate stationary solution of what properties the turbulent velocity field would satisfy. Instead, when doing experiments and simulations, what we have observed is that this is not the case. So we observe nonlinear exponents. So again, a power law with some exponent zeta q, which is not this linear function. And you can see that in these results, which are numerical simulations called DNS, and in experiments in the atmosphere. So at small values of q, we see a linear scaling behavior, but then as q increases, we see some deviations from this linear behavior. So what we're going to do is so these are some of the features we'd like to capture in a random model of turbulence. Another feature is the power spectrum density, which is also, so here we're looking at the velocity field in Fourier space, and when we look at its variance, it also behaves as a power law, this time in k, which is in Fourier space, and decaying with an exponent -5/3 approximately. And this is what we call the turbulent energy cascade, because energy is injected at the large spatial scales. This corresponds to the small Fourier scales. So this bump here corresponds to where energy is injected by the external force. This curve here at this region approximately corresponds to where energy is dissipated at the very small scales, and between these two ranges where energy is injected and it is dissipated, we roughly observe a power law decay with an exponent -5/3. And the same is observed in the simulations and in experiments. So these are the basic phenomenology, the basic statistical features of turbulent velocity fields, which we would like to capture in a simpler model. So I'll go back now to what elements we'll use for this description of random velocity fields in terms of a simpler model. So we'll start with fractional Gaussian fields, which can be defined as the action of some linear operator, pH, acting on a white noise. So all the information about the roughness of this velocity field is carried by the operator pH, which I will show to you briefly. So this is k to some exponent which involves age. There's a regularization at small k, which will make this velocity field have a finite variance. And then what's really important is that there's a linear operator pH acting on W. That's why I hide its explicit expression. And what we observe for this velocity field, for this field, the fractional Gaussian field, is that it obeys K41 for its absolute values. So if we compute increments of this field, they obey a power law with linear exponents QH, as Kolmogorov expected would happen for turbulent velocity fields. So this is a simple but a first description of turbulent velocity fields. Our question is then, can we capture this behavior, the fractional Gaussian field, through a PDE, which will have this as stationary solution when forced at the large scales? So these are basic elements in the phenomenology of turbulence. We have forcing at the large spatial scales, and as a solution, we have some random velocity field, which as a first approximation, we'll consider it to be the fractional Gaussian field. So this will not capture non-Gaussian effects, so higher order structure functions, but we'll get to that. So to answer that question, let's first look at this simple PDE, the transport PDE, but in Fourier space. So if we start from some initial condition G concentrated at the small value of K, this function, as time passes, this initial condition will be transported to large values of K. So if we add some forcing to this PDE and consider the same PDE now, not in Fourier space, but in real space, we'll observe that we have now a complex operator. So the operator responsible for the transport in Fourier space is this L, and it is now complex proportional to Ix. So this will make our velocity field complex. We're now in a 1D setting. So this 1D, so this U0 will be a rough velocity field, complex and in 1D. And it is forced by F, which is a random forcing, white in time, and correlated on the large scales in space. So the CF decays at a scale L. What happens is that because of this behavior, as the forcing which is injected at small k is transported to large k, we'll have at every instant a new forcing coming up, which is constantly acting in white noise in time. This will generate white noise. So as a result, we have a velocity field, dynamical velocity field forced at the large scales, which generates white noise. We can then mix these two elements. So we know how to generate a fractional Gaussian field as a linear operator acting on white noise. We know how to generate white noise dynamically from a large scale forcing. We can then use these two elements to make a fractional Gaussian field from a large scale forcing. So this answers the first question. How can we generate a fractional Gaussian field from a forcing at the large scales? And you can see that this equation is linear. So we're going to have a Gaussian velocity field, which looks very much like a fractional Gaussian field. So some of the properties, this fractional, we'll see what happens to it. This PDE, which generates a fractional Gaussian field, we have the same operator L, which is responsible for transport from small k to large k. So if we start from an initial condition concentrated at small k, the same effect is going to happen. We'll be moving to large k, and because of the pH operator, which controls the regularity of the solution, we'll have a new effect which depends on age and which will create the roughness of the resulting velocity field. We can also look at the power spectrum of the solution, which is the expectation value of the variance of u hat, u in Fourier space. And what we observe is that at small times, we'll only have small frequencies. This is what happens in the green curve. As time moves on, more higher frequencies will be populated. So we go to the yellow curve. As time moves on, we'll have higher and higher frequencies populated, going then to the blue curve. And so this is the injection scale at KL. This is the dissipative scale, indicated by 0 here. And at the dissipative scale, we'll reach a stationary state because the energy will be strongly depleted from these values on. Without viscosity, we would have an exact power law with this behavior k to the minus 2h minus 1, which in the case of turbulence, so we could set h to 1/3, and this would be exactly the value we observe in turbulence, which is minus 5/3. And we can show that this is an exact power law. So this is these elements show that we have a fractional Gaussian field as the result of a PDE forced on the large scales. And these already look like turbulence, at least on the level of the variance or second order structure functions. Let's now look at a video of those simulations. So what we observe here is that we have large correlations at small times, and as time moves on, smaller and smaller scales start to be populated. And then at some point, we'll reach a stationary state because of the action of viscosity. So no new smaller scales will be populated, but we'll have only new random velocity fields, all with the same roughness. Then you can see that we started from large correlation length, and as time moves on, we'll be moving to smaller and smaller correlation lengths and a rougher velocity field. So let's go now and review a bit. We have seen that we can act with a linear operator pH on a white noise, and that will generate a fractional Gaussian field. We have seen how to do that in a dynamical way. So U0 is that dynamical velocity field, which comes from a PDE forced on the large scales. We have observed that this velocity field follows a fractal scaling. So we have only a linear scaling in the exponents here, but we would like to observe more. We would like to observe multifractal exponents. And we can do that with this velocity field. This is a Gaussian multiplicative scale, which has been considered in the math literature. So the properties of applying an exponential of a white noise times a white noise are well known in the math literature. These two, U0 and U0, are the same random velocity fields, so they're strongly correlated, and these will generate non-Gaussian effects. And what we observe for the increments of these velocity fields is that they're strongly nonlinear with power law scaling, which follows some nonlinear function zeta q. So this will capture the multifractal behavior we observe, so that is deviations from the linear K41 scaling, which is Gaussian. So again, we will consider this transformation instead of this velocity field, and the PDE that comes from this, which is linear, we'll consider this other velocity field, and the PDE which comes from this construction. This new PDE is nonlinear, so we have now the same linear term as before, which has the transport term, which has the pH, the regularity term, but it has a new nonlinear term with an external force. So gamma is called the intermittency parameter. This controls how intermittent or how far from the linear scaling this the behavior this velocity field is going to be. And as if we take gamma to be 0, this is going to be reduced to the linear scaling, or to the Gaussian fractional Gaussian field. And we'll do numerical simulations of this PDE and compare the solutions with what comes from this velocity field. So from this if we can consider U0 to be the U0 from the white noise PDE and compute exactly the analytical properties or the increments of this construction, and then compare with what comes out from the numerical simulations of this. So we can, using U0 from the solution of our white noise PDE, we can compute its even moments. So the increments to the power 2q will behave as 2qh minus a correction proportional to gamma squared. So here we have these corrections are not linear in Q, and they contribute to the multifractal effects. And what is very important for the phenomenology of turbulence is that we have a non-trivial third order moment. So in turbulence, this known quantity, the third order scaling, this is proportional to 1. And in our case, we have a non-trivial behavior. In the Gaussian case, this would simply be 0. In this non-Gaussian case, we have some behavior which is different from 0 and which scales as 3h minus, again, a correction with gamma squared. So this already shows interesting non-trivial behavior, non-Gaussian behavior. And so this is what we call intermittent. And we're going to measure that, compare these two results of higher order moments, especially the third and fourth order moments. We call these in the literature skewness and flatness. So skewness is the third order increment, the expectation value of that normalized by the variance of the increments. And the fourth order increment is the flatness, again, normalized by its variance. And we expect these two to behave as power laws and with some quadratic with some quadratic behavior in gamma, the intermittency exponent. So these are results of our simulations. In blue, you can see our simulations with the largest values of viscosity, and in green, the smallest values of viscosity. So, and these are intermediate values of viscosity. As we decrease the value of viscosity, you can see that a larger range where an approximate power law can be observed. So as we decrease the viscosity, we expect that a larger and clearer power law range will be observed. And indeed, that's what happens. This is a log-log plot, so linear scaling here will correspond to some power law. And as we change the value of gamma, this is what happens in the inset and outside, we see that this scaling, this power law scaling, changes approximately as gamma squared, as we expected from the analytical calculations for a surrogate velocity field, which approximates our solution. The same happens in the fourth order moment. So for the flatness, we have again the same values of viscosity. So these are large values of viscosity. These are small values. And as we decrease the viscosity, we observe that a scaling range starts to be formed when we observe a power law. And again, if we change the value of the intermittency exponent gamma, we'll see that this slope changes from one value to the other approximately as gamma squared, as we expected from the analytical reasoning. So this means that, to conclude and present some perspectives, that we have presented a PDE that generates a fractional Gaussian field. This is the first element of the construction. This follows the phenomenology of turbulence, where we have forcing acting at the large scales, and as time passes, we'll develop rough velocity fields through the dynamics. This is what we call a linear cascade. We also have a nonlinear ansatz and a nonlinear PDE. This will allow us to build multifractal velocity fields which approximate even more the behavior of turbulence and can capture third order and fourth order scalings, which we actually observe in our simulations. These are important elements in order to reproduce turbulent velocity fields. And to conclude, we are working on the formalizations of these ideas in a novel collaboration working on. I'd like to thank you.
Thanks a lot. Are there any questions? Any comments? Yes, Milton.
So the PDEs that you described are 1D, and in principle turbulence is more. It happens in 3D, but of course you do a 1D projection of that. But I was wondering whether there is an heuristic reason for your choice of the 1D PDE as a projection of a 3D system or a 2D system.
So it was chosen as 1D just as a first step to a larger project. So one of the things we're working on is on higher dimensions, because this is what happens in 3D turbulence. In 2D turbulence, we'd have a different statistics. And in Berger's equation, which is like 1D turbulence, we'd have still different statistics. So it's one of the goals.
Okay.
Any more questions? Okay, so then I guess that's it. So let's thank him again.